Imagine for a moment that you've never seen your own face. You've touched it, felt the contours of your nose, your lips, your eyes, but you've never truly seen yourself. Now imagine walking to the edge of a still pond on a windless morning. You lean forward, and there, staring back at you, is a stranger. Except it's not a stranger. It moves when you move. It mirrors your confusion, your wonder, your sudden dawning realization. It's you. This moment happened somewhere in our deep past, perhaps 100,000 years ago, perhaps more. And in that instant, something extraordinary occurred. A human being became aware of themselves as an object in the world, not just a consciousness looking out, but a thing that could be looked at. A face, a body, a self. This is where our story begins, at the very first mirror, the surface of water, and the profound question it posed. What am I seeing when I see myself? Over the next few hours, we're going to explore one of the most familiar yet mysterious phenomena in the universe: reflection. We'll journey from ancient pools to quantum mechanics, from psychology to black holes, from the mirrors in your bathroom to mirrors that bend time itself. We'll discover that the simple act of seeing yourself contains within it the entire history of light, consciousness, and the cosmos. If you're ready for this journey, I invite you to settle in. And if you find yourself fascinated by what we explore together, consider subscribing to join us on future explorations of science and wonder. Leave a comment about what intrigues you most about mirrors. I read them all. Now, let's begin at the beginning, with water, stillness, and the first time a human saw their own eyes looking back. When water became a window. Water is everywhere on Earth. Rivers, lakes, ponds, puddles after rain. And for most of Earth's history, these surfaces have reflected the sky, the trees, the birds passing overhead. But for billions of years, no creature stopped to look at its own reflection and understand what it was seeing. The capacity for self-recognition, for seeing your image and knowing it represents you, is remarkably rare in nature. It requires not just eyes, but something more, a model of self, a sense that I exist as an entity separate from the world. Early humans, perhaps 500,000 years ago, certainly saw their reflections in water. But did they understand? Did Homo erectus, bending to drink from a stream, recognize the face rippling in the surface? Or did they see it as we might see a stranger, interesting perhaps, but not me? We don't know exactly when this shift happened, when reflection became recognition. But we know it did happen, because by the time humans were creating art, painting on cave walls, carving figures from stone, they were clearly depicting human forms with intention and understanding. They knew what humans looked like. They had studied faces, bodies, proportions, and one of the best ways to study a face is to see your own. Imagine the first time someone truly understood, perhaps a young woman by a calm pool, seeing her face clearly for the first time on an unusually still morning. The shock of recognition, the impossible strangeness of it. She raises her hand, the reflection raises its hand. She touches her face, the face in the water responds. This is not magic. This is not a spirit or a ghost. This is me. This moment of realization might seem simple to us now. We see ourselves dozens of times a day, in mirrors, in phone screens, in shop windows. But for that first human, it was a revelation that changed everything. Because once you can see yourself, you can begin to think about yourself differently. You become not just a subject experiencing the world, but an object in it. You have a face that others see, an appearance, an identity that exists outside your own mind. Water became humanity's first mirror, and in doing so, it became one of the first tools for self-awareness. A still pool wasn't just a place to drink. It was a window into something profound, the visible self. And we've been looking ever since. The Obsidian Mystery. But water has a problem. It ripples. It moves with the wind. It freezes. It evaporates. You can't carry it with you. You can't control it. So humans began to search for something more permanent, something that would hold their reflection steady. They found it in volcanic glass, obsidian, formed when lava cools so rapidly that it doesn't crystallize into the rough texture of normal rock, but instead solidifies into something smooth, glassy, almost alive with reflected light. Natural obsidian can be polished to an extraordinary shine. And when early humans discovered this, they created something revolutionary, the first portable mirrors. In Çatalhöyük, an ancient settlement in what is now Turkey, archaeologists have discovered obsidian mirrors dating back to around 6000 BCE. 8,000 years ago, someone carefully shaped and polished these pieces of volcanic glass until they could see themselves clearly. These weren't crude reflections in rough stone. These were true mirrors, smooth enough to show detail, permanent enough to last millennia. Imagine owning one of these mirrors 8,000 years ago. In a world without photography, without any way to capture images, this object would have been magical. It could capture your face and hold it, frozen, as long as you looked. It would show you aging, show you changing, show you the passage of time on your own features. What did they think they were seeing? Many ancient cultures believed that reflections held special power, that your reflection was connected to your soul, your essence, your life force itself. Some cultures believed that breaking a mirror could damage your spirit. Others thought reflections could be stolen, trapped, used in magic or curses. These beliefs weren't entirely irrational. In a sense, a reflection is a part of you. It's information about you, captured and displayed. In a world without scientific understanding of light and optics, it would be natural to wonder, where does the image come from? Why does it look exactly like me? Is it me, somehow, existing in two places at once? The obsidian mirrors of Çatalhöyük are among our earliest evidence that humans not only recognized themselves, but valued that recognition enough to create tools specifically for it. These weren't practical objects in the way a spear or a bowl was practical. They served a different need, the need to see, to know, to study the self. And that need, it turns out, was strong enough that humans would continue refining the mirror for the next 8,000 years, through bronze and silver and glass, through science and art and philosophy, always returning to that same fundamental desire to see the face looking back. The mystery that began with obsidian, what am I seeing when I see myself, remains with us today, even as we understand the physics. Some mysteries deepen when you know the answer. Bronze, copper, and vanity. Metal changed everything. By the Bronze Age, humans had learned to work copper, tin, bronze, and eventually silver and gold. And they discovered something remarkable. When polished to a high shine, these metals could reflect an image far clearer than water, far more reliable than obsidian. The mirror became an object of luxury, power, and beauty. In ancient Egypt, bronze mirrors were prized possessions, often buried with their owners to be used in the afterlife. These weren't simple discs of polished metal, they were works of art, with handles carved in the shape of lotus flowers, papyrus stems, or the goddess Hathor, who was associated with beauty and femininity. The wealthy carried them, consulted them, valued them as we might value jewelry or precious technology today. In ancient China, bronze mirrors became objects of deep cultural significance. They were perfectly round, symbolizing heaven, and often inscribed with poetry, wishes for longevity, or cosmic diagrams. To own a fine mirror was to own a piece of the universe's harmony, a tool for both practical grooming and philosophical contemplation. The Greeks and Romans, too, valued mirrors highly. Polished bronze or silver mirrors were marks of wealth and status. They appear in art, in literature, in mythology. Narcissus staring at his reflection until he wastes away. Medusa whose gaze can only be safely seen in the reflection of a polished shield. Perseus using a mirror to defeat her without meeting her eyes directly. But here's what's fascinating. These mirrors were expensive, difficult to make, labor-intensive to polish and maintain. They tarnished, they scratched, they required constant care. Owning a mirror meant you had resources, time, status. And because of this, mirrors became associated with vanity, with excessive concern for appearance, with superficiality, with the moral danger of self-obsession. Religious and philosophical traditions often warned against mirrors. They were tools of vanity, of pride, of distraction from higher concerns. The Latin word speculum meant both mirror and speculation. The idea that looking at yourself too much led to empty, self-centered thinking. Yet humans kept making them, kept using them, kept staring into polished metal to see their own faces. Because the desire to see yourself isn't really about vanity, though it can become that. It's about identity. It's about knowing how you appear in the world, understanding the face that others see when they look at you, recognizing the physical reality of your existence. Animals without self-recognition don't groom as carefully. Humans with mirrors could see asymmetry, could judge whether they looked healthy, could prepare themselves for social interaction. The mirror wasn't just a luxury, it was a tool for navigating social reality. By the time we reached the medieval period, mirrors had become so valuable that they were listed in wills, fought over in inheritance disputes, given as diplomatic gifts between nations. A fine mirror could be worth as much as a small estate. And yet, for all their value, these metal mirrors were still limited. They showed a dim, brownish, slightly distorted image. They weren't windows, they were approximations. The age of the true mirror, the glass mirror, was still to come. But already, humans had decided. Seeing yourself was worth almost any price. What the ancients thought they were seeing. The ancient Greeks were obsessed with vision. How do we see? What travels from object to eye? What is actually happening when we look at something, or when we look at our own reflection? Plato believed that vision worked through a kind of fire that emanated from the eyes. When you looked at something, your eyes projected rays outward that touched the object, and this touching allowed you to perceive it. A reflection, then, was these rays bouncing back from a polished surface. Your eyes reached out, touched the mirror, and returned with an image of yourself. Aristotle disagreed. He thought something traveled from the object to the eye, not fire, but some kind of influence or change in the medium between object and observer. Air or water, or whatever lay between you and what you saw, was altered by the object, and this alteration propagated until it reached your eye and created the sensation of sight. Neither was quite right, but both were grappling with something profound: the mystery of how information about the world reaches consciousness. How does the universe outside your skull become experience inside your mind? Euclid, the great geometer, studied mirrors mathematically. He understood that the angle at which light approached a mirror equaled the angle at which it reflected away. He could predict where an image would appear, how large it would seem, how distorted it might become in curved mirrors. He had the geometry right, but he still thought vision involved something projecting from the eyes. The truth, that light from the sun or from fire bounces off objects, enters the eye, and creates vision, wasn't fully understood in the West until the Islamic scholar Ibn al-Haytham wrote his book of optics around the year 1000. He demonstrated through careful experiment that light travels in straight lines, that it comes from luminous sources, that it bounces off surfaces in predictable ways, and that the eye is a receiver, not a projector. This was revolutionary. It meant that when you look at yourself in a mirror, you're seeing light that left the sun, traveled to your face, bounced into the mirror, bounced back to your eyes, and created the image you perceive. You are not projecting yourself into the mirror. The mirror is not capturing your soul. You are seeing yourself the way you see everything else, through reflected light. But even this correct understanding doesn't fully capture the strangeness of it. Because when you see yourself, you are seeing something unique, an object that is also the subject doing the seeing. The observer becoming the observed. The eye looking at the eye. Plato told a famous allegory about prisoners in a cave, chained so they can only see shadows on a wall. They mistake the shadows for reality, never seeing the true forms that cast them. Is a reflection like a shadow? Is it less real than the face it shows? Or is it exactly as real? Just light, just information, just patterns reaching your consciousness. The ancients didn't have electron microscopes or quantum mechanics or high-speed cameras. But they asked the right questions. What is vision? What is a reflection? What am I really seeing when I see myself? And in asking these questions, they set us on a path toward understanding something far stranger than they could have imagined. That light itself is both wave and particle. That reflection happens at the atomic scale through forces they couldn't have the atomic scale. Through forces they couldn't have dreamed of, that the simple mirror contains quantum mechanics, relativity, and the deep structure of physical law. They looked into mirrors and saw mysteries. We'll spend the rest of this journey discovering just how deep those mysteries go. What is light, really? To understand mirrors, we first need to understand what's actually bouncing off them. And that means we need to understand light itself, which turns out to be one of the most beautiful and bizarre things in the universe. Light is energy in motion. It's electromagnetic radiation traveling at the fastest speed anything can travel, roughly 300,000 kilometers per second, or about 186,000 miles per second. Nothing in the universe moves faster. In fact, the speed of light isn't just a speed limit, it's built into the fundamental structure of space-time itself. When you flip a light switch, photons begin their journey from the bulb. They radiate outward in all directions, bouncing off walls, furniture, your face, everything in the room. Some of those photons enter your eyes, strike the retina at the back of your eyeball, and trigger chemical reactions in cells called rods and cones. These reactions create electrical signals that travel along your optic nerve to your brain, where they're processed into what you experience as vision. This all happens so fast that it seems instantaneous, but it's not. There's a delay, tiny but real, between the light leaving an object and the moment you perceive it. When you look at something a meter away, you're seeing it as it was about 3 nanoseconds ago. That's 3 billionths of a second, imperceptible to human consciousness, but real nonetheless. Now, here's where it gets strange. Is light a wave or a particle? For centuries, scientists debated this question. Some experiments showed light behaving like waves, rippling, interfering with itself, bending around corners. Other experiments showed it behaving like particles, discrete packets of energy that could be counted individually. The answer, discovered in the early 20th century, is somehow both. Light is simultaneously wave and particle, existing in a quantum superposition of possibilities until it interacts with something. Each photon, each individual particle of light, is also a wave with a specific frequency and wavelength. Red light has a longer wavelength than blue light. Infrared has longer wavelengths than red. Radio waves have wavelengths measured in meters. X-rays have wavelengths smaller than atoms. But they're all the same phenomenon, electromagnetic radiation, traveling at the speed of light. When a photon hits your face, some of its energy is absorbed by your skin, converted into heat. But some photons bounce off, reflected back into the world. The color of your skin determines which wavelengths are absorbed and which are reflected. Dark skin absorbs more wavelengths and reflects fewer. Light skin reflects more and absorbs fewer. This is why dark objects warm up more in sunlight. They're absorbing more of the light's energy. So when light bounces off your face and into a mirror, you're dealing with photons that have already made one journey, from light source to face. Now they're about to make a second journey, from face to mirror, and then to your eyes. And in that journey lies everything we think we understand about reflection. But as we're about to discover, Even something as simple as a bouncing photon contains quantum mysteries that still puzzle physicists today. The bounce. A mirror seems simple. Light hits it, light bounces back. But let's slow down and look at what's actually happening at the atomic level, because it's far stranger than it first appears. When a photon approaches a mirror, it's approaching a surface made of atoms, usually glass coated with a thin layer of aluminum or silver. These metal atoms have a special property. Their electrons are loosely bound, free to move easily through the metal lattice. These are called free electrons, and they're the key to reflection. As the photon approaches, it's not really a tiny ball flying through space. Remember, it's also a wave, an oscillating electromagnetic field. This wave is made of two components, an electric field and a magnetic field, perpendicular to each other, rippling through space at the speed of light. When this electromagnetic wave reaches the metal surface, something remarkable happens. The oscillating electric field of the light wave starts pushing and pulling on the free electrons in the metal. These electrons, being charged particles, respond to electric fields. They begin to oscillate, to vibrate, in response to the incoming wave. And here's the crucial part. When electrons oscillate, they emit their own electromagnetic radiation. The vibrating electrons in the mirror's surface become tiny antennas, broadcasting a new electromagnetic wave back into space. This new wave travels away from the mirror at the speed of light, and it happens to be traveling in exactly the direction we call reflected. The angle at which the light approached equals the angle at which it departs. This is the law of reflection, known since ancient times, but now we understand why it's true. It's a consequence of how electromagnetic waves interact with free electrons. But not all the light reflects. Some of the photons transfer their energy to the metal atoms, causing them to vibrate more, which we experience as heat. Even the best mirrors absorb a small percentage of the light that hits them. A typical bathroom mirror reflects about 90% of visible light. The other 10% is absorbed, converted to thermal energy, lost. This is why if you shine a powerful laser at a mirror, the mirror will eventually heat up. It's why the mirrors in high-powered telescopes need sophisticated cooling systems. The absorbed energy has to go somewhere, and it goes into heat. Now here's something that might surprise you. The light that reflects off a mirror isn't quite the same as the light that arrived. The photons that bounce back are not literally the same photons that came in. The incoming photons were absorbed by the electrons, and new photons were emitted. It's a bit like catching a ball and throwing it back. The ball is the same, but the act of catching and throwing is a distinct process. The photon that left your face and the photon that enters your eye from the mirror are separated by this interaction, this absorption and re-emission. And in that gap, quantum mechanics gets very strange indeed. Because when you look closely at individual photons, the concept of the same photon becomes fuzzy. Identity at the quantum level doesn't work the way it does in the everyday world. A photon absorbed and a photon emitted might be indistinguishable in every measurable way, but are they the same? Quantum mechanics says the question doesn't quite make sense. What matters is the pattern, the information, the wave function, not the identity of individual particles. So when you look in a mirror, you're not seeing light that simply bounced. You're seeing new light, generated by electrons that were disturbed by old light, carrying the same pattern, the same information, the same image, but reconstituted, remade, fresh from the quantum realm. The mirror doesn't just reflect you. In a sense, it recreates you, photon by photon, every moment you look. The 8-nanosecond delay. Here's something most people never realize. When you look at yourself in a mirror, you're looking into the past. Not the distant past, not years or even seconds, but the past nonetheless. Let me explain. Light is fast, but it's not infinitely fast. It travels at 299,792,458 meters per second in a vacuum. In air, it's only slightly slower. In glass, it slows down more, about 2/3 its vacuum speed. But even at these tremendous velocities, light takes time to travel any distance. If you're standing 1 meter away from a mirror, the light from your face has to travel 1 meter to reach the mirror, then 1 meter back to reach your eyes. That's a total journey of 2 meters. At the speed of light, this takes about 6.7 nanoseconds, 6.7 billionths of a second. If you're standing 3 feet from a mirror, it's closer to 8 nanoseconds. This is an unimaginably short time. In 8 nanoseconds, a hummingbird's wings move less than a micrometer. A sound wave in air travels less than 3 millimeters. The electrical signals in your brain barely begin to propagate. Your conscious mind has no hope of perceiving this delay directly, but it's real. The face you see in the mirror is your face as it was 8 nanoseconds ago. You are literally seeing the past version of yourself. Now, you might reasonably ask, so what? 8 nanoseconds is meaningless. Nothing changes in that time. And for practical purposes, you're right. But philosophically, this reveals something profound about the nature of observation and reality. You can never see yourself now. You can never see anything now. All observation is historical. All perception is of the past. When you look at a friend across the table, you're seeing them as they were a few nanoseconds ago. When you look at the moon, you're seeing it as it was 130 seconds ago. When you look at the sun, you're seeing it as it was 8 minutes ago. When you look at the nearest star beyond our sun, Alpha Centauri, you're seeing it as it was 437 years ago. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. And when astronomers look at the most distant galaxies ever observed, they're seeing them as they were over 13 billion years ago, when the universe was young. Light is not just the carrier of images, it's the carrier of history. Every photon that enters your eye is a messenger from the past, bringing news of how things were when it began its journey. The mirror makes this particularly poignant because the object you're observing is yourself. You can never catch up to your own present moment. By the time the light from your face reaches your eyes, even if it's bouncing off a mirror right in front of you, that moment is already gone. You're always chasing yourself through time, always running just a few nanoseconds behind. This might seem like a strange thing to dwell on, but it's fundamental to understanding how the universe works. Causality, the relationship between cause and effect, is limited by the speed of light. Information cannot travel faster than light, so nothing can happen now across a distance. There is no universal now that spans space. Every point in space has its own timeline, and they connect only through the movement of light and other electromagnetic radiation. When you understand this, you begin to see mirrors differently. They're not just showing you yourself. They're showing you the history of yourself, preserved in photons that have made a journey through space-time to reach your eyes. You're watching yourself age at the speed of light, frame by frame, nanosecond by nanosecond, an endless movie of a person who is always already in the past. In a way, we're all living in the wake of ourselves, looking back at who we were, an instant behind reality forever. Why mirrors reverse left and right, but not up and down? This is the most famous mirror paradox, the one that has puzzled curious minds for centuries. Why do mirrors flip things horizontally but not vertically? When you raise your right hand in front of a mirror, the reflection raises what appears to be its left hand. But when you raise your hand above your head, the reflection's hand also goes up, not down. Why? What's special about left and right? Why does the mirror treat them differently than up and down? The answer is surprising, even shocking. Mirrors don't reverse left and right. They don't reverse anything. The mirror shows exactly what's in front of it, with perfect symmetry. The flip you perceive is something you're creating in your mind, not something the mirror is doing. Let me explain. When you look at yourself in a mirror, you're not seeing yourself as you'd see another person standing across from you. You're seeing yourself as if you've walked through the mirror and turned around. Imagine this. Suppose there's a person standing across from you, facing you. They raise their right hand, the hand on your left side from your perspective. Now imagine you walk around behind them and look at them from their perspective. Their right hand is now on your right side. This is not what happens in a mirror. In a mirror, when you raise your right hand, the reflection's right hand, which is on your right side, rises. The reflection has not walked around you. The reflection is showing you what you'd see if there were another U-shaped person standing inside the mirror facing outward, but that person is not rotated. They're flipped front to back. Here's the key insight. Mirrors reverse along the axis perpendicular to their surface. They flip front and back. They swap the space in front of the mirror with the space behind it. Imagine you're facing north, looking at a mirror on a north wall. In the reflection, it appears you're facing south. The wall that was behind you in reality appears behind your reflection. The mirror has flipped the north-south axis. But it hasn't touched the east-west axis, what you think of as left-right or the up-down axis. Those remain exactly as they are. So why does it seem like left and right are swapped? Because of how you imagine positioning yourself. When you imagine going into the mirror, your brain automatically rotates you 180 degrees around a vertical axis, the way you'd turn to face the opposite direction. But the mirror doesn't rotate you. It flips you front to back without rotation. To see what the mirror actually does, try this. Lie down on your side in front of a mirror. Orient yourself so your head and feet are parallel to the mirror surface. Now look at your reflection. Is your head where your feet should be? No, head is still head. Feet still feet. But what was in front of you is now behind your reflection, and what was behind you is now in front. The mirror has flipped the axis perpendicular to itself, the only axis it ever flips. The left-right reversal is a cognitive illusion. It happens because humans have bilateral symmetry. Left and right are special to us, and because we naturally imagine social interactions as involving rotation rather than front-back flipping. When we see a face, we imagine how we'd orient ourselves to have that perspective, and that imagination involves turning around. This is why text in a mirror appears backward. Not because left and right are swapped, but because the front of each letter, the ink side, has been flipped to face the opposite direction. If you hold up a transparent sheet with letters written on it, and you look at it from behind, the letters appear reversed, same as in a mirror, because you're seeing the back surface of the letters instead of the front. Mirrors don't have special rules for horizontal versus vertical. They have one simple rule: reverse the direction perpendicular to the surface. Everything else, all the apparent paradoxes, comes from how our brains interpret that reversal. And once you understand this, mirrors become a little less magical, but a lot more interesting. What happens to the light that doesn't reflect? We've talked about the light that bounces off a mirror, carrying your image back to your eyes. But what about the light that doesn't bounce? Because even the best mirrors don't reflect 100% of the light that hits them. Where does the rest go? The answer involves one of the most fundamental laws of physics, the conservation of energy. Energy cannot be created or destroyed. It can only change forms. So the light energy that doesn't reflect must go somewhere. It goes into heat. When a photon strikes a mirror and is absorbed rather than reflected, its energy is transferred to the atoms of the mirror. The electrons absorb the photon's energy and move to a higher energy state. But they can't stay there. Almost immediately, they drop back down to a lower energy state, releasing the excess energy, usually as heat, the random vibration of atoms. This is why, if you touch a mirror that's been in bright sunlight, it feels warm. Some of the sun's light has been absorbed, converted to thermal energy, and that energy has raised the temperature of the glass and metal. This is true of every surface, not just mirrors. Everything that light touches absorbs some of that light and converts it to heat. Dark objects absorb more light, that's why they're dark, and therefore convert more light energy into heat. This is why wearing black on a sunny day makes you hotter than wearing white. White fabric reflects most visible light. Black fabric absorbs most visible light. The absorbed light becomes heat in the fabric, which conducts to your skin, which makes you uncomfortable. Now, let's think about this in terms of entropy, the measure of disorder in a system. The second law of thermodynamics tells us that entropy always increases in a closed system. The universe trends toward disorder, toward equilibrium, toward heat death. When light reflects off a mirror, the process isn't perfectly efficient. Some light is absorbed, some is scattered in random directions, some heats the mirror. The ordered directional energy of incoming photons becomes partially disordered. Some reflected photons, some heat, some waste. This is entropy in action. In fact, every time energy changes forms, some becomes heat. This is why every machine, every process, every engine ever built loses some energy to heat. Friction, resistance, absorption, these are all manifestations of the second law. Energy spreads out, becomes less concentrated, less useful. Heat is the graveyard of energy. Eventually, in the unimaginably distant future, the universe will reach what's called heat death. All energy will have been converted to evenly distributed thermal energy. No gradients will remain, no hot spots and cold spots, no stars burning, no structure, just endless uniform warmth approaching absolute zero as the universe expands. At that point, no more work can be done. No more reflections, no more light bouncing off mirrors, no more observers to see anything. Just equilibrium. But we're not there yet. We won't be for trillions upon trillions of years. For now, stars burn, light bounces, and mirrors reflect. And in that reflecting, even with its imperfections and losses to heat, we get to see ourselves, to study the world, to build telescopes that look billions of light years into space. The fact that mirrors aren't perfect, that they lose energy to heat, is a reminder that we exist in a universe governed by the second law of thermodynamics. Everything is running down, slowly, toward equilibrium. But in the meantime, in this brief window of existence, while stars still burn and mirrors still reflect, we get to look. We get to see our faces, our world, the cosmos. And that seems like a pretty good trade for a little waste heat. The photons that don't reflect aren't lost. They're just doing something else, warming atoms, adding to entropy, participating in the long, slow heat death of everything. And the photons that do reflect, they're messengers, carrying images across space and time, making vision possible, making mirrors magical even when you understand the physics. Both are part of the same story. Energy transforming, entropy increasing, the universe slowly winding down, but not yet, not quite yet, still reflecting. When physics got weird. By the end of the 19th century, physicists thought they had light figured out. It was a wave, an electromagnetic oscillation traveling through space. The equations worked beautifully. Maxwell's laws predicted everything about light's behavior. Radio waves, visible light, X-rays, all just electromagnetic waves at different frequencies. Then in 1900, Max Planck discovered something that didn't fit. When he studied how hot objects glow, why a piece of metal glows red when heated, then orange, then white, the math only worked if he made a strange assumption. Energy comes in discrete packets, not smooth continuous amounts. He called these packets quanta. Planck himself didn't believe this was physically real. He thought it was a mathematical trick, a convenient fiction that happened to give the right answer. But it wasn't a trick. In 1905, Einstein showed that light itself comes in these packets, individual particles of electromagnetic energy. He called them photons. When light hits metal, it doesn't smoothly transfer energy like a wave washing over a beach. Individual photons strike individual electrons, transferring their energy in discrete quantum jumps. This explained a photoelectric effect, a phenomenon that had puzzled physicists for decades. But this created a crisis. Light is a wave. The interference patterns prove it. But light is also particles. The photoelectric effect proves it. How can something be both? The answer quantum mechanics eventually provided is unsettling. Light is neither wave nor particle, or perhaps both, or perhaps something stranger that we don't have words for. It exists in a superposition of possibilities. The wave describes the probability of where a photon might be detected. The particle is what you find when you look. Before observation, there's no fact of the matter about where the photon is. After observation, it's definitely here or there. You found it. The act of observing collapses the wave of probability into a specific outcome. Now, apply this to a mirror. When a single photon approaches a mirror surface, quantum mechanics says something extraordinary. The photon exists in a superposition of being reflected and being absorbed. Both outcomes are possible. The wave function describes the probability of each. Only when you detect the photon, when it enters your eye or hits a detector, does one outcome become real. You might think, well, obviously some photons reflect and some absorb, and we just can't predict which individual photon does what. That's how probability works with coins too. You flip it, you get heads or tails. Unpredictable, but one or the other happens. But quantum mechanics is stranger than that. Before measurement, it's not that the photon has already decided to reflect or absorb and we just don't know which. It genuinely hasn't decided. It's in both states simultaneously until the moment of measurement forces a definite outcome. This isn't philosophy. This is experimentally verified physics. Particles in superposition states behave differently than particles in definite states. You can test it. You can measure it. The universe really is this strange. So when you look in a mirror, you're not just seeing reflected light. You're seeing the outcome of countless quantum measurements, each photon collapsing from superposition into a definite state, reflected or absorbed at the moment of interaction. Reality crystallizes into definiteness, one photon at a time, every moment you look. The mirror isn't just a passive surface. It's a stage where quantum possibilities become classical certainties, where the strange rules of the microscopic world give rise to the familiar reflection you see every morning. The photon's decision. Let's zoom in on a single photon's journey to understand how truly strange this gets. A photon leaves a light bulb in your bathroom, travels through air, strikes your face. Most photons are absorbed. Their energy converts to heat in your skin. But some photons bounce off. The ones that bounce travel toward the mirror on your wall. Now the photon approaches the mirror's metal surface. Let's say it's aluminum, one of the most common reflective coatings. At the surface are aluminum atoms, each with 13 electrons orbiting the nucleus. Some of those electrons are loosely bound, free to move through the metal lattice. As the photon, which remember is also a wave, reaches the surface, its electromagnetic field begins interacting with these free electrons. Here's what quantum mechanics tells us. The photon has a probability of being reflected and a probability of being absorbed. For a good mirror, maybe 90% chance of reflection, 10% chance of absorption. But until the interaction is complete, both outcomes exist in superposition. The photon is neither definitely reflected nor definitely absorbed. It's in a quantum state that includes both possibilities. Physicist Richard Feynman developed an extraordinary way to think about this. He showed that you can calculate the probability of the photon being reflected by imagining that the photon takes every possible path simultaneously, bouncing off every possible point on the mirror surface, even taking absurd curved paths through space. Each possible path contributes to the final probability. Most paths cancel each other out through quantum interference, but the paths that contribute constructively give you the classical trajectory. The angle of incidence equals the angle of reflection. The photon doesn't choose one path. It takes all paths at once in superposition and the interference between these paths produces the definite outcome you observe. Now here's the truly mind-bending part. The photon that enters your eye after bouncing off the mirror is not the same photon that left your face. When a photon is absorbed by an electron in the mirror, that photon ceases to exist. Its energy is transferred to the electron. Then, almost immediately, the electron drops back to its lower energy state and emits a new photon. This new photon has the same energy, the same wavelength, the same direction as the old photon, but it's not the same photon. At the quantum level, identical particles are truly indistinguishable. There's no hidden label that marks one photon as different from another. If two photons have exactly the same properties, they are, in every measurable sense, the same. Not similar, actually, fundamentally indistinguishable. So in one sense, the photon that enters your eye is the same as the photon that left your face. In another sense, it's a completely new photon, freshly minted by the electrons in the mirror. Both descriptions are equally valid. Quantum mechanics doesn't distinguish between them. This gets even stranger when you consider virtual particles, quantum fluctuations in the vacuum of empty space. Even when no light is present, the quantum vacuum seethes with virtual photons popping into and out of existence, borrowing energy from the uncertainty principle for impossibly brief moments. These virtual particles can interact with real photons and real electrons. The mirror isn't just reflecting light through empty space, it's reflecting light through a quantum foam of virtual particles, each contributing tiny corrections to the reflection process. None of this is perceptible in everyday experience. When you look at yourself in the mirror, you see a clear, classical image. But that image emerges from an underlying quantum reality of superposition, probability, indistinguishable particles, and virtual fluctuations. The smooth, predictable world we see is built on a foundation of irreducible strangeness. And yet, it works. Quantum mechanics makes the most accurate predictions in all of science. It's been tested to absurd precision, predictions matching experiments to 10 decimal places or more. This weirdness isn't speculation. It's how the universe actually operates. Every reflection you've ever seen is the visible outcome of quantum mechanical processes operating at scales far too small to see, making billions of decisions every second. Or perhaps not making decisions at all, but simply existing in us. Superposition until you look, until measurement collapses possibility into actuality, until the photon that might have been absorbed becomes the photon that was definitely reflected. The mirror shows you yourself, but it does so through quantum magic, one indeterminate photon at a time. The mirror at the quantum scale. To really understand what happens at a mirror surface, we need to go deeper still, down to the level of atoms and the electromagnetic force that governs their behavior. An atom consists of a nucleus surrounded by electrons. These electrons don't orbit like planets around a sun. That's an outdated model. Instead, they exist in quantum orbitals, probability clouds describing where the electron is likely to be found. These orbitals have specific shapes and energy levels, determined by the quantum mechanical wave equation. In a metal like silver or aluminum, the outermost electrons aren't bound to individual atoms. They form what's called an electron sea, a shared pool of electrons that can move freely throughout the metal. This is why metals conduct electricity. Apply a voltage, and these free electrons flow. This is also why metals reflect light so well. When the oscillating electric field of a light wave hits the metal surface, it pushes and pulls on these free electrons. The electrons respond almost instantaneously, accelerating back and forth in response to the light's electromagnetic field. And here's the key: accelerating charges emit electromagnetic radiation. This is a fundamental law of electromagnetism. Anytime you accelerate an electric charge, it radiates. The electrons in the mirror surface, forced to oscillate by the incoming light wave, become tiny broadcasting antennas. They emit their own electromagnetic waves, and these emitted waves are what we perceive as reflected light. The new wave has the same frequency as the incoming wave. The electrons oscillate at the same frequency as the light that's driving them. This is why mirrors don't change the color of light. Red light comes in, red light comes in, red light bounces out. The wavelength is preserved because the frequency of oscillation is preserved. But not all materials have free electrons. Glass, for instance, is an insulator. Its electrons are tightly bound to atoms. When light passes through glass, it interacts with these bound electrons differently. The light slows down, which is why glass has a refractive index greater than 1, and some light is absorbed. This is why glass alone doesn't make a good mirror. You can see through it, but reflections are faint. To make a mirror, you coat glass with metal. The glass provides a smooth, rigid surface. The metal provides the free electrons that do the actual reflecting. In older mirrors, mercury was used, then silver. Modern mirrors often use aluminum. It's cheaper, nearly as reflective, and doesn't tarnish as quickly. The layer of metal is incredibly thin, just a few hundred nanometers, less than the wavelength of visible light. Yet this thin film is enough to reflect the vast majority of photons that strike it. Now consider what happens at the boundary between glass and metal, or between air and metal. At this boundary, the electromagnetic properties of the materials change abruptly. The wave nature of light means that this boundary isn't a perfectly sharp line. Light doesn't just stop at one atom and start at the next. Instead, there's a transition region, an evanescent field that extends slightly beyond the physical surface. When light undergoes total internal reflection, trapped inside a material like glass or water, this evanescent field extends into the region beyond the surface. If you bring another material close enough, within the range of this evanescent field, some light can tunnel across the gap and escape. This is called frustrated total internal reflection, and it's a purely quantum mechanical phenomenon with no classical analog. The mirror is a place where quantum mechanics, electromagnetism, and materials science all meet. The familiar image you see emerges from electrons being pushed around by electromagnetic fields, from the quantum mechanical properties of atoms and orbitals, from the collective behavior of trillions upon trillions of particles acting in concert. And all of this happens in the time it takes light to travel a few nanometers, femtoseconds, quadrillionths of a second. In the time between one moment and the next, in an interval far too brief for consciousness to register, the quantum ballet of reflection unfolds, and you see yourself looking back. Virtual particles and the vacuum. Here's something that might surprise you. Empty space isn't empty. Even in a perfect vacuum, with no atoms, no light, no matter of any kind, the quantum vacuum seethes with activity. This is one of the most profound predictions of quantum field theory, the marriage of quantum mechanics and special relativity. According to Heisenberg's uncertainty principle, you cannot simultaneously know both the energy of a system and the time interval with arbitrary precision. The more precisely you know one, the less precisely you can know the other. This relationship is written as delta E times. Delta T is greater than or equal to h bar over 2, where h bar is Planck's constant divided by 2 pi. What this means is extraordinary. For very short times, energy can fluctuate wildly. The universe can borrow energy from nothing, as long as it pays it back quickly enough. And when energy spontaneously appears, it can manifest as particle-antiparticle pairs, a photon and its antiparticle another photon, or an electron and a positron, or any of the other particles of nature. These are called virtual particles. They pop into existence, exist for a fleeting moment, and then annihilate back into vacuum. They never last long enough to be directly observed, but they have real, measurable effects. One such effect is the Casimir effect. Take two metal plates, bring them very close together in a vacuum, just nanometers apart. The plates will be pushed together by a measurable force. Why? Between the plates, Only virtual particles with wavelengths small enough to fit can pop into existence. Outside the plates, virtual particles of all wavelengths can exist. This creates a difference in the quantum vacuum energy between the inside and outside, producing a net force pushing the plates together. This has been measured. It's real. The vacuum between the plates has less quantum activity than the vacuum outside, and this difference creates pressure. Now think about what this means for a mirror. Light reflects off a mirror surface, traveling through what we think of as empty space. But that space is filled with virtual photons, constantly appearing and disappearing. These virtual photons can interact with real photons. The real photon can absorb a virtual photon, briefly gain energy, then emit it again. This process contributes tiny corrections to the path and energy of the real photon. When physicists calculate the properties of electrons, their mass, their charge, how they interact with light, they have to account for virtual particles. An electron is constantly surrounded by a cloud of virtual photons that it emits and reabsorbs. These virtual photons slightly change the electron's effective mass and charge. The corrections are small, but they've been measured to extraordinary precision. Theory and experiment agree to better than 1 part in a billion. So when you look at a mirror, you're seeing light that has traveled through a quantum vacuum buzzing with virtual activity. The smooth, predictable path of light from your face to the mirror to your eye is actually the average of countless quantum fluctuations, virtual interactions, brief departures from classical behavior that mostly cancel out but leave subtle traces. There's another profound implication. The vacuum has energy. The quantum fluctuations we've been discussing represent real energy density in empty space. This vacuum energy might be connected to dark energy, the mysterious force causing the universe's expansion to accelerate. We don't fully understand this yet, but the quantum vacuum's properties could have cosmic significance. Some physicists speculate that the entire universe might be a quantum fluctuation, a region of space where energy fluctuated into existence and hasn't yet decayed back to vacuum. If so, then everything, including you, including mirrors, including light itself, is borrowed energy from the quantum foam, temporarily structured into matter and fields, persisting for billions of years but ultimately destined to return to vacuum. When you look at yourself in a mirror, photons travel through this strange quantum vacuum, bounce off a surface governed by quantum mechanical rules, and enter your eyes to create an image. The solid, reliable reflection you see is built on a foundation of virtual particles, uncertainty, borrowed energy, and the fundamental weirdness of quantum field theory. The universe whispers its deepest secrets in the space between you and your reflection, if only you listen closely enough. The Glassmakers of Venice. For thousands of years, humans made mirrors from polished metal. Bronze, silver, copper, all required constant polishing, all gave dim, distorted reflections, all tarnished with time. Then, in 13th century Venice, something revolutionary happened. Glassmakers discovered how to make mirrors from glass. The technique came from the Islamic world, where scholars and artisans had been experimenting with glass and metal coatings for centuries. But the Venetians perfected it, industrialized it, and turned it into one of the most valuable secrets in European history. The process was kept on the island of Murano, just off Venice's main islands. All glass production was moved there. Officially, because of fire risk, glass furnaces could easily burn down Venice's wooden buildings. But the real reason was control. On an island, secrets were easier to keep. Workers could be monitored. Defectors could be stopped before they reached the mainland. The Venetian mirror-making technique involved coating the back of a piece of glass with a tin mercury amalgam. Mercury is liquid at room temperature, but when mixed with tin powder, it forms a paste that can be spread on glass. As it dries, it creates a reflective layer that adheres to the glass surface. The glass protects the reflective coating from tarnish and damage, while the metal coating provides the actual reflection. The result was miraculous. For the first time in history, people could see themselves clearly, in color, without distortion. Venetian mirrors were sharper, brighter, and more durable than any metal mirror ever made, and they were worth a fortune. Venice treated mirror-making knowledge as a state secret. The penalty for revealing the techniques to outsiders was death. The penalty for trying to leave Venice to work elsewhere was also death, or at minimum, imprisonment and the murder of family members left behind. This wasn't paranoia. This was economic warfare. Other European powers desperately wanted the secret of Venetian mirrors. France, in particular, sent spies, offered bribes, and eventually succeeded in luring some Venetian glassmakers to Paris, where they established rival production. The Venetian government sent assassins. Some defectors were murdered, others disappeared. A few made it and began teaching the French their techniques, breaking Venice's monopoly. But for over 150 years, from the late 13th century through the 15th century, Venice dominated the European mirror trade. A single large mirror could cost as much as a ship. Mirrors were given as diplomatic gifts, dowries for royal marriages, treasures listed alongside gold and jewels in estate inventories. Owning a mirror meant you were wealthy. Owning a large mirror meant you were extraordinarily wealthy. The glassmakers of Murano became rich and privileged. They couldn't leave the island, but they had special legal status, exemptions from certain laws, prestige. They were treated almost as nobility, except they were prisoners of their own expertise. This strange mix of wealth, status, and confinement defined their lives. And through it all, they kept making mirrors, sheet by sheet, coating by coating, producing objects that seemed like frozen magic. People who had never seen their own faces clearly suddenly could. Nobles could check their appearance before audiences. Women could apply cosmetics with precision. Artists could study their own faces for self-portraits. The mirror transformed self-awareness, vanity, art, and social presentation in ways both profound and mundane. And behind all of it, the glassmakers of Venice worked in secret, their techniques protected by death, their products worth fortunes, their island prison a place of creativity, danger, and extraordinary craft. Tin, mercury, and poison. The Venetian mirror-making process was not just secret, it was deadly. Mercury, the key ingredient in the reflective coating, is a neurotoxin. Prolonged exposure causes tremors, mood swings, cognitive decline, kidney damage, and death. The glassmakers of Murano were slowly being poisoned by their craft. The process worked like this. First, you needed a sheet of perfectly smooth glass. This alone required extraordinary skill. Glass had to be blown, then flattened, then polished to eliminate bubbles and irregularities. Even small imperfections would show in the final mirror. Next came the toxic part. Tin and mercury were combined into a viscous amalgam. This amalgam was spread carefully on one surface of the glass. Then the glass was placed horizontally to let the coating settle evenly. Mercury vapors filled the workspace. The artisans breathed them in, hour after hour, day after day. As the amalgam dried, the mercury partially evaporated, leaving behind a tin coating bonded to the glass. But much of the mercury remained, and more would be released over the mirror's lifetime. The mirror itself was slightly toxic to own, and extremely toxic to make. Descriptions of mirror makers from this period note their shaking hands, their irritability, their tendency to die young. The phrase "mad as a hatter" comes from a similar phenomenon. Hat makers used mercury compounds to treat felt, and mercury poisoning caused neurological symptoms that resembled madness. Mirror makers suffered the same fate. They knew it was dangerous. The symptoms were obvious. But the money was extraordinary, and in an age without social safety nets or alternative employment, many chose to continue despite the risks. Some tried to work faster, to limit their exposure. Others accepted early death as the price of their craft. By the 17th century, When Venice's monopoly was breaking down and other European centers began producing mirrors, the mercury tin process spread. So did the occupational hazards. French mirror makers at the Manufacture Royale de Glace de Miroir died at higher rates than other artisans. Insurance records show shorter life expectancies. Medical treatises noted the tremors and cognitive decline. And yet production continued because demand was insatiable. Everyone who could afford a mirror wanted one, and those who couldn't afford one aspired to it. The mirror became a status symbol, a luxury item, a marker of wealth and refinement. The toxic cost was borne by the workers, invisible to the aristocrats admiring their reflections. It wasn't until 1835 that a German chemist named Justus von Liebig developed a safer process, silvering glass with silver nitrate instead of mercury tin amalgam. This method was cheaper, safer, and produced even better mirrors. Within a few decades, mercury mirrors became obsolete. But by then, thousands of artisans had spent their lives breathing mercury vapors, trading their health for the ability to show others their own faces. The beautiful, clear Venetian mirrors that hung in palaces and noble houses across Europe were products of slow poisoning, occupational death, and the terrible calculus of risk versus reward that has always characterized dangerous professions. Today, antique Venetian mirrors are collector's items, valued for their craftsmanship and historical significance. But they're also toxic waste. Many still contain mercury in their coatings. Handle them carefully. The poison persists, centuries later, a reminder that beauty and danger often intertwine. Versailles and the Hall of Mirrors. In 1678, King Louis XIV of France commissioned the most extravagant room in European history, the Hall of Mirrors at the Palace of Versailles. It would contain 357 mirrors, each one a technological marvel, together creating a space of unprecedented brilliance and grandeur. This was more than interior decoration. This was a political statement. At the time, mirrors were still phenomenally expensive. A large mirror cost as much as a naval warship. Venice still dominated production, and France still depended on Venetian imports for quality mirrors. Louis XIV wanted to break that dependence. He wanted France to master mirror making, and he wanted the world to know France had succeeded. So he invested enormous resources into industrial espionage, luring Venetian glassmakers to France with promises of wealth and protection. Some came willingly. Some were coerced. Some were murdered by Venetian agents for their betrayal. But enough survived to teach French artisans the techniques. By the 1660s, France had established its own mirror manufacture, producing glass that rivaled Venice's finest work. The Hall of Mirrors was the proof. Each mirror was placed opposite tall arched windows overlooking the palace gardens. Sunlight would stream through the windows and reflect off the mirrors, filling the room with light. At night, thousands of candles would be lit, and their light would multiply in the mirrors, turning the hall into a glittering spectacle of reflected fire. The effect was overwhelming. Visitors described feeling disoriented, amazed, diminished by the room's grandeur. The mirrors created an illusion of infinite space. You couldn't always tell where the room ended and reflections began. The ceiling was painted with scenes glorifying Louis XIV's reign, and these paintings reflected in the mirrors below, multiplying the king's image and achievements throughout the space. This was the mirror as propaganda. Louis XIV understood that power is not just military or economic, it's also aesthetic and psychological. A king who could casually display 357 mirrors was demonstrating wealth beyond imagination. He was showing that France could produce what previously only Venice could produce. He was proving French technological and artistic supremacy. And it worked. The Hall of Mirrors became legendary. Foreign dignitaries were brought there to be awed. Treaties were signed there, including, much later, the Treaty of Versailles ending World War I. The room became synonymous with French power and culture. But beyond the politics, there's something profound about what Louis XIV created. He built a room where you could never escape your own reflection, or the reflections of others. Everywhere you looked, you saw yourself. The crowd, the light, the grandeur. It was a space designed to overwhelm the senses, to make you feel both seen and lost in seeing. In a way, the Hall of Mirrors is the ultimate expression of the mirror's power over human psychology. We're drawn to reflections. We seek them out. We use them to understand ourselves and to present ourselves to others. Louis XIV took that impulse and amplified it to the extreme, creating a space where reflection wasn't just a tool, but an environment, where self-image and political image merged into a single, overwhelming experience. The mirrors were silent propaganda, whispering constantly, "Look at what we can do. Look at how much light we can command. Look at yourself, here, in the presence of all this splendor." And millions of visitors, then and now, have looked and been transformed by looking. When everyone could see themselves. For most of human history, seeing your own face clearly was a rare privilege. Metal mirrors were expensive and gave poor reflections. Glass mirrors were even more expensive. Only the wealthy could afford them. The average person might see their reflection in water or a polished pot, but rarely with clarity. This changed in 1835 when Justus von Liebig, a German chemist, invented a new silvering process. Instead of using toxic mercury tin amalgam, Liebig's method deposited pure silver onto glass using a chemical reaction. Silver nitrate solution, mixed with reducing agents, would coat glass with a thin, uniform layer of metallic silver. The process was safer, cheaper, and produced superior mirrors. Within decades, mirror production industrialized. What had once been artisan craft became factory production. Prices plummeted. By the late 19th century, ordinary middle-class families could afford mirrors. By the early 20th century, even working-class homes had them. For the first time in history, most people could see themselves clearly, daily, throughout their lives. This changed human psychology in ways we're still understanding. Before widespread mirrors, your face was something you experienced mostly through others' reactions. You knew roughly what you looked like, but you didn't have constant access to your own image. Now you did. You could study your face, track changes, notice asymmetries, compare yourself to ideals of beauty. The rise of mirrors coincided with the rise of modern advertising, fashion industries, and cosmetics. These weren't coincidental. When people can see themselves clearly, they become more concerned with appearance. Industries emerged to serve and to create that concern. Mirrors became furniture. Bedroom mirrors, bathroom mirrors, hallway mirrors, handheld mirrors for purses. Barbershops and salons installed multiple mirrors so customers could see all angles. Clothing stores added three-way mirrors. The ability to see yourself became expected, unremarkable, essential to daily life. But this ubiquity came with psychological costs. Studies show that people in cultures with widespread mirror use are more prone to appearance-based self-criticism. Eating disorders correlate with mirror exposure. Body dysmorphia, obsessive concern over perceived flaws, is a modern phenomenon, emerging alongside universal mirror access. The mirror democratized vanity. It also democratized self-awareness. People could watch themselves age, year by year, line by line. They could see the effects of illness, stress, joy, time. The face became a text you could read, a record of life lived, visible in unprecedented detail. Psychologists developed the mirror test for self-recognition, using mirrors to determine which animals possess self-awareness. Human infants develop mirror self-recognition around 18 to 24 months of age, the moment they realize the baby in the mirror is them. This milestone marks a leap in cognitive development, the emergence of a concept of self as an object in the world. In a sense, widespread mirror access gave humanity a collective mirror moment. We became a species constantly aware of our own appearance, constantly monitoring how we look, constantly comparing image to ideal. This has driven enormous economic activity, social pressure, psychological distress, and also genuine self-knowledge. The mirror shows you truth, how you actually look, not how you imagine you look. That truth can be difficult. We tend to think we look slightly better than we do. Cameras and mirrors reveal reality, and sometimes reality disappoints. Yet we keep looking. We can't resist. The mirror has become one of the defining objects of modern life, as essential as the wheel or the book. From royal luxury to industrial commodity to psychological necessity, the mirror's journey tracks humanity's changing relationship with self-image, identity, and a strange, compelling desire to see ourselves seeing. The mirror test. In 1970, psychologist Gordon Gallup placed chimpanzees in front of mirrors and watched what happened. At first, the chimps treated the reflection as another chimp, threatening it, making social gestures. But after a few days, something shifted. They began using the mirror to examine parts of their bodies they couldn't normally see, picking food from their teeth, grooming hard-to-reach spots. They had figured it out. The image was them. To test this conclusively, Gallup anesthetized the chimps and placed a red mark on their foreheads, somewhere they couldn't see without a mirror. When they woke and looked in the mirror, they immediately touched their own foreheads, trying to remove the mark. They understood that mark is on me, not on the reflection. This became known as the mirror test, the gold standard for measuring self-recognition in animals. It's harder than it seems. Most animals never pass. Dogs, cats, birds, fish. They see reflections as other animals, rivals or companions. They never recognize themselves. But a few species do pass. Great apes, chimpanzees, bonobos, orangutans, gorillas, though not all individuals. Elephants pass, using their trunks to touch marks on their heads. Dolphins pass, examining marked parts of their bodies in mirrored walls. And remarkably, magpies pass, the only birds known to show clear self-recognition. What does passing the mirror test mean? It suggests the animal has a concept of self as a physical entity. They understand, I have a body that looks a certain way, and that reflection is my body. This is different from just being conscious or intelligent. Many smart animals fail the mirror test. It's specifically about self-awareness, the ability to think about yourself as an object. Human infants develop this ability between 18 and 24 months old. Before that age, babies treat their reflection like another baby, smiling at it, reaching for it. After that age, they recognize themselves and become suddenly more interested in their appearance. They'll pose, make faces, become self-conscious about how they look. This moment is profound. It's when the child develops a theory of self, an understanding that I exist as an entity that others can see and judge. This is the foundation for empathy, for understanding that others have perspectives different from yours, for complex social reasoning. But here's the fascinating part. Passing the mirror test isn't binary. Some animals show partial recognition. They seem confused, uncertain. Some animals change their behavior in front of mirrors without touching marks. And some species might have self-awareness, but express it differently than we expect. The mirror test assumes visual self-recognition matters. But what about species that navigate primarily by smell or sound? A bat might have rich self-awareness, but never recognize itself visually. An octopus might be self-aware in ways we can't measure with mirrors. The test reveals something profound about those who pass it, but it might hide equally profound awareness in those who fail. Still, for species that do pass, including us, the mirror becomes a tool for self-discovery, a way to see yourself as others see you, a window into the strange experience of being both subject and object, both the one who looks and the thing being looked at. The stranger in the mirror. In rare neurological conditions, people lose the ability to recognize themselves in mirrors. They look at their reflection and see a stranger an imposter, someone else entirely. This is distinct from simply not liking how you look. These patients genuinely don't perceive the reflection as themselves. They might argue with it, accuse it of mimicking them, become distressed by its presence. They know intellectually that it's a mirror, but the emotional recognition, the deep, automatic sense of "that's me," is gone. This often occurs in dementia or after brain injury affecting specific regions. The right hemisphere, particularly areas involved in face recognition and body awareness, seems crucial for mirror self-recognition. Damage that can disrupt the ability while leaving other cognitive functions intact. In Capgras syndrome, patients believe loved ones have been replaced by identical imposters. Sometimes this extends to their own reflection. They see their face but feel convinced it's not them. It's a duplicate, a copy, something uncanny and wrong. The perception is accurate, but the emotional connection is severed. Another striking condition is mirror self-misidentification, where patients don't just fail to recognize themselves, but develop elaborate explanations. They might believe the person in the mirror is a relative, a stranger living in their walls, or a persecutor watching them. They treat the mirror as if it's a window to another room. What does this tell us about normal mirror recognition? That it's not automatic or simple. Your brain has to integrate visual information from the mirror, match it with your internal body representation, connect it to your sense of self, and generate the emotional response of recognition. If any step fails, the whole experience falls apart. For most of us, this process is so seamless we never notice it happening. We look in a mirror and instantly, effortlessly know, "That's me." But this knowing is an achievement of neural computation, a feat of brain integration that can be disrupted by disease or damage. There's also phantom mirror phenomena, the opposite problem. Some people experience phantom reflections, seeing their image in surfaces that aren't reflective. Windows, walls, even blank spaces seem to show their face looking back. This is typically associated with psychosis or severe anxiety disorders. The brain's self-monitoring systems become overactive, projecting the self into the environment. These conditions reveal how fragile and constructed our sense of self really is. The person you see in the mirror isn't a simple, direct perception. It's a creation of your brain, assembled from sensory data, memory, body sense, and emotional response. When the assembly process breaks down, the mirror shows a stranger. And perhaps this is true even for those of us with intact recognition systems. The face we see is always partially a construction, filtered through our expectations, our mood, our self-concept. We don't see ourselves objectively. We see ourselves through the lens of who we think we are. The mirror might show reality, but what we perceive is always an interpretation. Phantom reflections and mirror therapy. V.S. Ramachandran, a neuroscientist studying phantom limb pain, had a strange idea. Patients who'd lost an arm or leg often felt their missing limb was still there, and worse, that it was frozen in a painful position. They'd try to move it and couldn't. The phantom limb felt paralyzed, cramped, agonizing. Medication rarely helped. The pain was real, generated by the brain, but there was no physical limb to treat. Ramachandran wondered, what if he could trick the brain? He built a simple box with a mirror inside. The patient would place their intact hand in one side and look at its reflection while positioning their missing limb's residual limb on the other side. When they looked in the mirror, they saw two hands, one real, one reflected. But visually, it appeared as if both arms were present and symmetrical. Then Ramachandran asked them to move both hands. The real hand moved. The reflection moved. And suddenly, the phantom hand felt like it was moving too. The pain often released immediately. Patients who'd suffered for years found relief in minutes just by looking at a reflected hand and believing it was their phantom limb moving freely. This worked because of how the brain constructs body awareness. The brain integrates visual, tactile, and proprioceptive information to create a sense of where your body is and what it's doing. When there's a conflict, the visual system says the arm is moving, but there's no sensory feedback from an arm. The brain gets confused. In some patients, this confusion manifests as phantom pain. The mirror resolves the conflict. The visual system sees movement, and the brain accepts it, updating its model of the body. The phantom limb unfreezes. The pain disappears, not because anything physical changed, but because the brain's internal model changed. This technique, now called mirror therapy, is used worldwide for phantom limb pain, stroke rehabilitation, and complex regional pain syndrome. It demonstrates something profound. Pain isn't just in the body. It's in the brain's representation of the body. Change the representation, change the pain. The mirror becomes a tool for rewriting neural maps, for teaching the brain new stories about the body. Patients practice daily, moving their intact limb while watching the mirror, training their brain to accept new patterns. Over time, the phantom limb can feel more normal, less painful, sometimes even disappear as the brain adjusts its body map. This reveals how malleable our sense of embodiment really is. The body you feel isn't exactly the body you have. It's the body your brain thinks you have, constructed from sensory input and prediction. The mirror can hijack that construction, inserting false information that feels entirely real. In virtual reality experiments, people can be made to feel they inhabit different bodies, taller, shorter, different genders, even non-human forms. The brain adapts rapidly. If visual input consistently shows you have 4 arms, you start to feel you have 4 arms. If a rubber hand is stroked in sync with your real hand, you start to feel the rubber hand is yours. This is called the rubber hand illusion, and it demonstrates that body ownership is surprisingly easy to manipulate. We think of our bodies as solid, fixed, unquestionable. But to the brain, the body is a hypothesis, constantly updated by sensory data. The mirror is one of the simplest tools for testing and changing that hypothesis. Reflection becomes not just a way to see yourself, but a way to reshape yourself, at least in the brain's internal model, which is where you actually live. The Funhouse Effect. Distorted mirrors disturb us in a way that few other optical illusions do. A funhouse mirror that stretches you tall or compresses you wide triggers immediate discomfort, even though you know it's fake. Why? Because it violates your body schema, your brain's internal model of what your body should look like. This model is built from a lifetime of sensory integration: what you see, what you feel, how you move. It's usually stable, reliable, consistent. Then you look in a distorted mirror, and suddenly your proportions are wrong. Your head is enormous. Your legs are tiny. You look alien, monstrous, impossible. Consciously, you know it's an illusion. But unconsciously, your brain reacts with confusion and unease. The visual input doesn't match the stored body model. For most people, this is amusing, briefly disorienting, but harmless. We can laugh at funhouse mirrors because we know they're not real reflections. But for people with body dysmorphic disorder, every mirror is a funhouse mirror. BDD is a psychiatric condition where people become obsessed with perceived flaws in their appearance. Flaws that are often minor or entirely imagined. They see themselves as grotesque, deformed, unbearable to look at, and no amount of reassurance changes this perception. The mirror becomes an enemy. Patients check their reflection compulsively, spending hours examining the flaw, trying to fix it, comparing themselves to others. Or they avoid mirrors entirely, unable to bear what they see. The distress is profound. BDD has one of the highest suicide rates of any psychiatric disorder. What causes this distorted perception? It's not fully understood, but it involves the same neural systems that process faces and bodies, combined with anxiety circuits that amplify threat detection. The brain's internal model of how I should look becomes unrealistic, and any deviation from this model triggers distress. Treatment often involves mirror exposure therapy, sitting in front of a mirror for extended periods without performing checking behaviors. This gradually reduces the anxiety response and helps patients see themselves more accurately. The mirror, used therapeutically, can retrain perception. Eating disorders also involve distorted mirror perception. Patients with anorexia often see themselves as larger than they are. This isn't metaphorical, it's a literal perceptual distortion. When asked to estimate their body size, they consistently overestimate. Brain imaging shows altered activity in regions that process body shape and size. The mirror shows reality, but their brains construct a different image from that visual information. Interestingly, these distortions can be temporary and context-dependent. Studies show that people judge their body size differently depending on mood, recent experiences, and social context. After seeing images of thin models, people rate themselves as larger. After exercise, some rate themselves as smaller. The mirror shows the same reflection, but perception shifts. This reveals something unsettling. We don't see ourselves objectively, even in accurate mirrors. We see ourselves through filters of expectation, emotion, and cognitive bias. The mirror offers raw data, but our brains interpret that data, and the interpretation is malleable, vulnerable to distortion. For most of history, people rarely saw themselves. Perhaps this protected them from the psychological burden of constant self-observation. Now we see ourselves dozens of times daily: mirrors, phone screens, video calls, photos. We're always under our own surveillance. And for some people, this constant visibility becomes oppressive. The mirror that was supposed to show us truth becomes a source of anxiety, distortion, and pain. The reflection we see is never just what's there. It's filtered through who we think we are, who we fear we are, who we want to be. The Funhouse mirror exaggerates this openly. The regular mirror does it silently. Mirrors and vanity. For millennia, religious and philosophical traditions have warned against mirrors. They represent vanity, self-obsession, spiritual danger. Narcissus stared at his reflection until he died. Medusa's gaze could only be safely viewed in reflection. Mirrors were tools of both salvation and danger. Early Christian writers condemned mirrors as instruments of pride. Islamic scholars debated whether mirrors distracted from devotion. Buddhist teachings warned against attachment to the physical self. The mirror revealed the body, the temporary vessel, the illusion of separate selfhood. To gaze too long was to forget the deeper truth beyond appearances. These weren't entirely wrong. There's psychological research showing that mirror exposure increases self-focused attention, which correlates with anxiety, depression, and narcissistic behavior in vulnerable individuals. The more time you spend looking at yourself, the more you tend to criticize what you see and worry about how others perceive you. But is this the mirror's fault or ours? The mirror doesn't judge. It shows exactly what's there, no more, no less. The judgment comes from us. We look at ourselves and compare to impossible standards, photoshopped images, idealized fantasies. We see flaws and magnify them. The mirror becomes a tool of self-criticism. Yet mirrors also enable self-care and social functioning. You check your appearance before important meetings, not from vanity, but from practical necessity. Appearance affects how others treat you, whether we like it or not. The mirror lets you navigate this reality. Animals without self-recognition don't groom as effectively. Humans with mirrors can maintain hygiene, present themselves appropriately, participate more successfully in social hierarchies. The problem isn't the mirror. It's the culture that surrounds it. In societies that heavily emphasize physical appearance, that monetize beauty, that create billion-dollar industries around appearance anxiety, mirrors become weapons of self-judgment. In societies with different values, mirrors are neutral tools. The rise of selfies is sometimes called peak narcissism. Billions of people photographing themselves constantly, curating their image for public consumption. But is a selfie more narcissistic than commissioning a painted portrait? Something wealthy people did for centuries? Maybe we're not more vain. Maybe vanity is just more visible, more accessible, democratized along with the mirror itself. There's also evidence that moderate self-reflection is psychologically healthy. People who never think about their appearance or how they're perceived often struggle socially. Total self-focus is pathological, but so is total self-neglect. The mirror enables a middle path, enough self-awareness to function socially without obsession. Philosophers have long noted the paradox. Self-knowledge requires self-observation, but self-observation can become self-obsession. The mirror literalizes this paradox. It gives you the means to see yourself, which is necessary for certain forms of understanding, but it also enables endless loops of self-scrutiny. Perhaps the wisdom isn't to avoid mirrors, but to use them skillfully. Look enough to know yourself, not so much that you forget everything else. See yourself clearly, then look outward. The reflection is information, not identity. And the face you see is just one small part of what you are, the part that happens to be visible, the surface, the light reflecting boundary between your inner world and the outer one. Everything that matters most is invisible in mirrors. The acoustic mirror. Not all mirrors reflect light. Some reflect sound. Before radar was invented, militaries needed ways to detect approaching aircraft. In the 1920s and 30s, Britain built enormous concrete structures shaped like parabolas, acoustic mirrors, designed to focus sound waves the way optical mirrors focus light. They were massive, some over 20 feet tall, positioned on hilltops facing the sea. An operator would stand at the focal point with a listening device. When an aircraft approached, its engine noise would reflect off the concrete surface and concentrate at the focus, amplified and directional. The operator could hear planes coming from miles away, long before they were visible. The physics is identical to optical reflection. Sound waves are pressure waves in air. When they strike a hard surface, they bounce back. The angle of incidence equals the angle of reflection, just like light. A curved surface can focus these reflected waves to a point, concentrating the acoustic energy. These acoustic mirrors worked surprisingly well, until radar made them obsolete almost immediately. Radar could detect aircraft much farther away, in any weather, day or night. The concrete mirrors became relics of a brief technological moment, giant sculptures now weathered and silent on the British coast. But acoustic reflection is everywhere. Concert halls are designed with careful attention to how sound reflects off walls and ceilings. The shape of the room determines whether music sounds rich and full or muddy and echoing. Parabolic microphones use curved reflectors to focus distant sounds. You see them on NFL sidelines, pointed at quarterbacks to capture their calls. Whispering galleries are architectural spaces where sound reflects off curved walls so efficiently that a whisper at one point can be heard clearly dozens of meters away. St. Paul's Cathedral in London has a famous whispering gallery. Stand on one side and whisper at the wall. Someone on the opposite side hears you perfectly, while people between you hear nothing. The sound travels along the curved wall by repeated reflections. Animals use acoustic mirrors too, though biological ones. The parabolic shape of a barn owl's face acts as a sound mirror, focusing faint noises from prey onto the owl's ears. Each ear receives slightly different timing and intensity, allowing the owl to locate a mouse in complete darkness with extraordinary precision. Dolphins and whales use echolocation, emitting clicks and listening to reflections. They're using the ocean and objects in it as acoustic mirrors, building mental maps from reflected sound. The bat does the same in air, navigating and hunting entirely by acoustic reflection. What's fascinating is how deeply parallel optical and acoustic mirrors are. Both follow the same geometric laws. Both can focus, distort, concentrate, or scatter. Both allow perception at a distance. You can see or hear things far away by detecting reflected waves. Both have been used by evolution and by human technology to extend sensory range. yet they feel completely different to us. We trust our eyes more than our ears. Visual mirrors seem more real than acoustic ones. But this is just sensory bias. A bat probably trusts acoustic reflections more than visual ones. To a dolphin, echolocation creates as rich a perceptual world as vision creates for us. The principle of reflection is universal. It applies to any wave phenomenon. Light, sound, water waves, seismic waves, even quantum matter waves. Whenever a wave encounters a boundary, some portion reflects. The universe is filled with reflections, most of them invisible to human perception. We notice the optical mirrors because we're visual creatures. But we're surrounded by acoustic mirrors, every wall, every surface, constantly reflecting pressure waves. You hear your own voice partly through sound conducted through your skull, and partly through sound that exits your mouth, reflects off the environment, and returns to your ears. The voice you hear isn't the voice others hear, because you hear a different mix of direct and reflected sound. In a sense, you never hear your own true voice. Just like you never see your own face, except in reflection. Acoustic mirrors remind us that reflection isn't unique to light. It's a fundamental feature of waves in general, and of the universe's basic architecture. The gravitational mirror. Einstein's general relativity tells us that gravity isn't a force in the traditional sense. It's a curvature of space-time itself. Mass bends the fabric of the universe, and objects follow the curved paths through that bent space. This has a remarkable consequence. Gravity can bend light. Light always travels in straight lines, but straight means following the geometry of space-time. If space-time is curved, light curves with it. This is called gravitational lensing, and it turns massive objects into gravitational mirrors. When light from a distant star passes near a massive galaxy, the galaxy's gravity bends the light's path. To observers on Earth, the star appears in a slightly different position than it would otherwise. If the alignment is perfect, the star's light can bend around all sides of the galaxy, creating a ring of light, an Einstein ring. The galaxy acts as a lens or a mirror, concentrating and redirecting light through pure gravitational geometry. This isn't just theory. Astronomers observe gravitational lensing constantly. The Hubble Space Telescope has captured spectacular images of distant galaxies distorted into arcs and rings by foreground mass. These lensing events allow us to study galaxies too far and faint to see directly. Their light is amplified by gravitational mirrors along the way. Black holes are the ultimate gravitational mirrors. At the event horizon, the boundary beyond which nothing can escape, space-time is so severely curved that light orbits the black hole. There's a region called the Photon Sphere, just outside the event horizon, where light can travel in circles around the black hole forever. If you were at the Photon Sphere and looked to the side, you'd see the back of your own head. Light from you would circle the black hole and return. You'd be trapped in a hall of infinite reflections, seeing yourself from every angle simultaneously. Images distorted by relativistic effects into a strange, kaleidoscopic self-portrait. Of course, you'd also be torn apart by tidal forces and falling toward the horizon, so sightseeing would be difficult. But theoretically, the black hole creates a perfect gravitational mirror, one that reflects light not by bouncing it off electrons, but by bending space-time so drastically that light loops back on itself. Gravitational lensing is now used as a tool. By measuring how background galaxies are distorted by foreground mass, astronomers map dark matter, the invisible mass that makes up most of the universe's matter. Dark matter doesn't emit light, doesn't absorb light, can't be seen directly, but it has mass, so it curves space-time, so it lenses light. The distortions reveal where dark matter is and how much there is. In this way, gravitational mirrors let us see the invisible. They're tools for mapping the universe's hidden architecture, and they work on the largest scales imaginable, across billions of light years, using entire galaxy clusters as mirrors. Einstein predicted all this in 1915, but thought it would never be observable. The effects seemed too small, too distant. Then, in 1919, Arthur Eddington observed stars near the Sun during a solar eclipse. Their positions had shifted, exactly as Einstein predicted. Light from stars was bending around the Sun's mass. The Sun was a gravitational lens. This observation made Einstein world-famous overnight. Here was proof that space and time were not fixed backgrounds but dynamic, curved, responsive to mass and energy. And the proof came from light, acting in ways that seemed impossible under Newtonian physics. Gravitational mirrors remind us that reflection doesn't require a surface. It requires only a way to redirect light. Electrons do it through electromagnetic interaction. Curved spacetime does it through geometry. Both are mirrors, both follow laws of reflection, both reveal information about the universe. When you look at gravitationally lensed images from Hubble, you're seeing ancient light that has been reflected by the structure of spacetime itself, curved by invisible mass, bent around galaxies, focused by gravity into shapes nature never intended. You're seeing the universe using itself as a mirror. Time mirrors and temporal reflection. Here's a bizarre idea from cutting-edge physics. What if you could reflect light in time instead of space? A normal mirror reflects light across space. Light approaches from one direction, leaves in another direction. The spatial path reverses. But what if a material's properties changed so suddenly that light reflected temporally, its frequency shifted forward or backward in time's dimension? This is called a time mirror. And while it sounds like science fiction, physicists have recently created them in laboratories. The concept works like this. Light traveling through a material depends on that material's refractive index, how much the material slows light down. If you could change the refractive index everywhere simultaneously, faster than light can travel across the material, you'd create a temporal boundary. Light would encounter a sudden change in the medium's properties, not in space, but in time. At a spatial mirror, light reflects because it encounters a boundary in space. Air meets glass. Glass meets silver. At a temporal mirror, light reflects because it encounters a boundary in time. The medium's properties change suddenly everywhere at once. What happens to the light? Its frequency shifts. Light that was red becomes blue, or vice versa. The wavelength changes, but the light's position doesn't. This is time reflection, the temporal analog of spatial reflection. In 2023, researchers achieved this using metamaterials, engineered materials with properties that can be switched rapidly. They sent light into the material, then changed its refractive index in nanoseconds. The light inside experienced a temporal boundary and reflected, its frequency shifted, just as theory predicted. Why does this matter? Because it reveals something fundamental. Reflection is about boundaries, not surfaces. Any boundary in the properties of space or spacetime can reflect waves. Most boundaries are spatial. This is glass, that is air. But boundaries can also be temporal. The medium was like this, now it's like that. And if boundaries can exist in time, can they exist in other dimensions? Could there be boundaries in phase space, in quantum fields, in dimensions we haven't discovered yet? Each could reflect waves in strange new ways. Time mirrors also have potential applications. They could be used to create optical isolators, devices that let light through in one direction but not the other, without magnetic fields. They might enable new kinds of lasers, telecommunications devices, or quantum computing components. But beyond applications, time mirrors expand our concept of what reflection is. For thousands of years, humans have understood mirrors as physical surfaces that bounce light. Then we discovered gravitational mirrors, curved spacetime bending light. Now we're creating time mirrors, temporal boundaries shifting light's frequency. Reflection is more general than we thought. It's a phenomenon that can occur across space, across time, through gravity, through quantum fields. Anywhere there's a wave and a boundary, there can be reflection. And this hints at something deeper. The universe is full of boundaries we haven't noticed yet. Boundaries between quantum and classical, between matter and field, between one vacuum state and another. Each boundary is a potential mirror for some phenomenon, reflecting something in ways we might not recognize as reflection at all. When you look at an ordinary mirror, you're seeing the most familiar type of reflection, light bouncing off electrons in metal. But you're also seeing an example of a universal principle that extends far beyond the human scale, far beyond optical light, into realms where time itself can act as a reflecting surface. The simple mirror on your wall is a window into the universe's deep structure, a reminder that the most familiar phenomena often conceal profound strangeness. The antimatter mirror. In particle physics, there's a symmetry called charge parity, or CP symmetry. It says that if you swap every particle with its antimatter partner and flip space like a mirror image, the laws of physics should stay the same. Antimatter is like matter's reflection. An electron has negative charge. A positron, its antimatter counterpart, has positive charge. A proton has positive charge. An antiproton has negative charge. Mass and spin stay the same, but charge flips. If you could build a human from antimatter, they'd look identical, behave identically, think identically, until they touched regular matter, at which point both would annihilate in a burst of energy. According to CP symmetry, an antimatter universe would function just like ours. The laws of physics don't care whether you're made of matter or antimatter. The universe is supposed to be symmetric, mirrored across this fundamental divide. But there's a problem. The universe we observe is made almost entirely of matter. Where's all the antimatter? In the Big Bang, matter and antimatter should have been created in equal amounts. They should have annihilated each other completely, leaving only energy, no atoms, no stars, no us. Yet here we are. Something broke the symmetry. In the 1960s, physicists discovered CP violation. Certain rare particle interactions don't respect the mirror symmetry between matter and antimatter. The universe has a slight preference for matter over antimatter. For every billion antimatter particles created in the early universe, there were 1,000,000,001 matter particles. The billion pairs annihilated. The one leftover matter particle survived. And from those survivors, everything we see is built. Every star, every planet, every atom in your body. We exist because the universe isn't perfectly mirrored. The antimatter reflection is slightly fainter, slightly less stable. The symmetry is broken, and that breaking is why there's something rather than nothing. This is one of the deepest mysteries in physics. Why is CP violated? Why does the universe prefer matter over antimatter? We don't fully know. The standard model of particle physics includes CP violation, but the amount it predicts is too small to explain the observed matter-antimatter asymmetry. There must be additional sources of CP violation we haven't discovered. Experiments are ongoing. The Large Hadron Collider studies how particles and antiparticles decay differently. Neutrino experiments look for CP violation in neutrino oscillations. Somewhere in these differences lies the explanation for why we exist. The antimatter mirror is a broken mirror. The reflection isn't quite exact. And that imperfection saved the universe from annihilating itself into pure radiation. If you could somehow meet your antimatter twin, a being made of positrons, antiprotons, and antineutrons, arranged in the same patterns as your atoms, you'd look identical. You'd think identically. You'd be perfect mirrors of each other, until you touched. Then, in a fraction of a second, you'd both convert entirely into energy. Gamma rays and heat, following Einstein's EMC. Your combined mass would become pure light. This is the most efficient energy conversion possible, far more efficient than nuclear fusion or fission. Matter-antimatter annihilation converts 100 of mass into energy. It's one reason antimatter is studied for potential spacecraft propulsion, though storing antimatter is phenomenally difficult since it annihilates on contact with any normal matter. The universe contains some antimatter. Cosmic rays include antiprotons and positrons. PET scanners in hospitals use positron emission, radioactive isotopes that emit antimatter particles, which then annihilate with electrons in your body, producing gamma rays that reveal metabolic activity. But large-scale antimatter is absent. No antimatter stars, no antimatter galaxies. The universe chose a side, and we're the consequence of that choice, living in a cosmos that's not quite symmetric, not quite mirrored, where one side of a fundamental reflection is vastly dominant. The antimatter mirror reveals that even the universe's deepest symmetries can be broken. And sometimes, those breaks are what make existence possible. Lacan's mirror stage. French psychoanalyst Jacques Lacan proposed a striking theory. The moment a child recognizes themselves in a mirror is the moment the ego is born. Between 6 and 18 months, an infant passes through what Lacan called the mirror stage. Before this, the infant experiences the world as a blur of sensations, no clear boundary between self and environment, no unified sense of I. Then they see themselves in a mirror, and something extraordinary happens. The fragmented, uncoordinated experience of being a body suddenly becomes whole. The infant sees a complete, bounded, unified image. They see Gestalt, a coherent form, and they identify with it. That's me. I am that thing, that whole, that image. But here's Lacan's crucial insight. This identification is fundamentally alienating. The mirror shows you something you can never actually be, an object seen from outside, a complete image, a third-person perspective on yourself. You are not that image. You're the messy, fragmented subjectivity behind the eyes, the chaos of sensation and thought and feeling. But the mirror convinces you that you are that external form. The ego, according to Lacan, is this misidentification. It's the story you tell yourself about being a unified, coherent self, a story based on an image, a reflection, a surface. And this story is necessary for functioning in the world, but it's also a lie. You're not the smooth, whole image. You're the turbulent interior. The mirror creates a split, the I that sees and the me that is seen. These two are never fully reconcilable. You can never see yourself as you actually are, only as an object, an image, a reflection. And this gap between subject and object, between the one who looks and the thing being looked at, generates a fundamental alienation. We spend our lives trying to reconcile the internal experience of being ourselves with the external image others see. We curate our appearance, manage our presentation, obsess over how we're perceived. All because the mirror convinced us, early in life, that we are an image to be looked at. Lacan's theory is controversial, but it captures something true about the strangeness of self-awareness. Animals that pass the mirror test don't just recognize themselves, they develop a new kind of self-consciousness. They become aware that they are objects in the world, visible to others, possessing an appearance. This is both empowering and burdensome. You gain the ability to think about yourself, to plan how you present yourself, to navigate social reality. But you also gain self-consciousness in the negative sense, anxiety about being seen, judged, evaluated. The mirror creates the conditions for both pride and shame. And perhaps this is why mirrors have always been morally complicated. Religious traditions warned against them, not just because of vanity, but because of this deeper issue. The mirror creates an ego, a self-image, an identification with surface rather than depth. It pulls you out of unself-conscious being and into self-aware performance. Of course, we can't go back. Once you've seen yourself, you can't unsee. The mirror stage is irreversible. The ego, once formed, persists, We live in the gap between inner experience and outer image, forever divided, forever trying to reconcile the reflection with the reality. The mirror on your wall doesn't just show you your face, it shows you the fundamental structure of self-consciousness, the split, the gap, the alienation that comes with being both subject and object, both the one who sees and the one who is seen. The ship of Theseus reflection. There's an ancient thought experiment called the ship of Theseus. A ship returns from voyage. One plank is rotted, so it's replaced. Next voyage, another plank is replaced. This continues until, eventually, every single original plank has been swapped out. Is it still the same ship? If not, when did it stop being the same ship? After the first plank? The 1000th? When exactly did identity change? Now apply this to the face you see in the mirror. Every atom in your body is replaced over time. The carbon, nitrogen, oxygen, hydrogen, all exchanged through metabolism, breathing, eating, excreting. Your skin cells slough off and regenerate. In 7 to 10 years, most of the atoms that currently make up your body will be gone, replaced by new atoms from food, air, water. The face you see today is built from different atoms than the face you saw a decade ago. Yet you recognize it as your face. You trace continuity through the changes. You see the same person. But what makes it the same? Not the matter, that's been swapped out completely, like the ship's planks. Not the exact appearance, you've aged, changed, scarred. What persists? Perhaps it's the pattern. The specific arrangement of atoms, the structure, the information. Even though the matter changes, the pattern propagates forward in time. Each new atom takes the place of an old atom in the same functional position. The pattern self-replicates using new materials. But patterns change too. Your face ages, wrinkles form, hair grays. The pattern itself is not static. So maybe identity is continuity of process rather than continuity of substance or form. You are not the atoms or the arrangement, you're the ongoing process of metabolizing, repairing, aging, existing. The ship is the sailing, not the wood. You are the living, not the body. Yet when you look in a mirror, you see a static image, a frozen moment. The process made visible as form. And you call it me? But which me? The one from 10 years ago, made of different atoms. The one right now, already being replaced. The one 10 years hence, unrecognizable yet continuous. The mirror doesn't answer. It only shows the present moment, which is already the past by the time light reaches your eyes. You're seeing yourself as you were nanoseconds ago, built from atoms that are already leaving, in a pattern that's already changing. Philosophers have struggled with personal identity for millennia. What makes you the same person you were as a child? Not the body. That's entirely replaced. Not your memories. Those are reconstructed, unreliable, constantly revised. Not your personality. That changes with experience, age, context. Some argue there is no continuous self. The you that existed yesterday is gone. Today's you is a new entity that shares memories and patterns with yesterday's, but isn't literally the same being. Each moment, you die and are replaced by someone almost identical. Others argue that continuity of consciousness is enough. As long as the stream of experience persists, as long as each moment connects to the next through memory and causation, identity persists. The mirror complicates this because it shows you from outside. It reveals that your sense of stable identity, the feeling that you are you, continuous through time, doesn't match the physical reality. Your body is a river constantly flowing, never the same water twice. Yet the river has a name, a course, an identity. Are you the water or the river? The atoms or the pattern? The substance or the process? When you look at your reflection, you're looking at one frame of a movie that's been playing your entire life. The previous frames are gone. The future frames don't exist yet. This frame will be gone in an instant. Yet somehow, across all these frames, you persist. Changed but continuous. Different but the same. The mirror shows you this paradox made visible. How can you be both changing and constant? Both substance and process. Both the ship's planks and the ship itself. There's no final answer, only the ongoing mystery of identity confronting itself in reflection. The problem of other minds. When you look at someone else's reflection in a mirror, what are you seeing? You see their image, their face, their body, their appearance. But are you seeing them? This is a version of the problem of other minds, one of philosophy's most persistent questions. You have direct access to your own consciousness. You know what it feels like to be you, the stream of thoughts, the sensations, the inner experience. But you can never have direct access to anyone else's consciousness. You can see their behavior, hear their words, observe their expressions. But you can never experience what it's like to be them. So how do you know other people are conscious at all? Maybe they're philosophical zombies, beings that look and act like conscious people but have no inner experience. They're just biological machines, responding to stimuli, producing outputs, but with no one home inside. You can't prove this isn't true. Every piece of evidence you have for others' consciousness is indirect. They say they're conscious, but a sophisticated robot could say that too. They behave as if they're conscious, but behavior can be programmed. They have brains like yours. But how do you know brains generate consciousness? You've only got one data point, yourself. This is deeply unsettling. Most of us assume other people are conscious. We treat them as if they have inner lives as rich as our own. But this is an assumption, an inference, a leap of faith. It's not knowledge in the strict philosophical sense. Now, add a mirror to this thought experiment. You look at your reflection and recognize consciousness looking back, because it's you. But when you look at someone else's reflection, you're seeing it from the same perspective you see your own, a face, an image, an appearance. Yet you can't access their experience the way you access your own. The mirror shows both reflections identically, but your epistemic access is radically different. Some philosophers argue that the best explanation for others' behavior is that they're conscious like you. It's simpler, more elegant, more consistent with what we observe. This is called the argument from analogy. They're similar to me in structure and behavior, so they're probably similar in consciousness too. But this isn't proof. It's a probabilistic inference. And for people with certain neurological conditions or philosophical temperaments, this inference breaks down. Solipsism, the belief that only your own mind exists, is unfalsifiable. You can't disprove it because all your evidence comes through your own perceptions. The entire universe might be your dream or hallucination. Others might be figments. There's no way to verify external reality from inside your own consciousness. The mirror reflects this problem beautifully. When you see yourself, you see from inside and outside simultaneously. You're both subject and object, both the experiencer and the experienced. But when you see another person, you're only outside. You see their object side, their appearance, but you can never access their subject side, their experience. They remain fundamentally opaque. This creates what philosopher Thomas Nagel called the view from nowhere problem. You can imagine what it's like to be someone else, but you're still imagining it from your perspective. You can never actually adopt their perspective because you can't step outside your own consciousness. Even if you could somehow swap bodies, you'd experience their body through your consciousness. You still wouldn't know what it's like to be them experiencing their body through their consciousness. The mirror literalizes this impossibility. Two people can stand in front of a mirror. Both see their reflections. But each person sees their reflection from inside their own private experience. The mirror shows both the same thing, reflected images, but generates completely different experiences for each observer. And there's no way to compare those experiences directly. No way to know if you're even seeing the same thing. This is why consciousness remains philosophy's hardest problem. We can study brains, map neurons, trace signals. But the subjective experience, the what it's likeness, remains private, inaccessible, known only to the one who experiences it. The mirror is a perfect metaphor for this barrier. It shows surfaces, appearances, the visible. But it can never show the invisible inner life, the consciousness that looks out from behind the reflected eyes. Can you ever see yourself as others see you? Here's a simple question with no simple answer. Can you ever see yourself the way others see you? At first, this seems easy. Just use two mirrors at an angle or take a photo. Now you're seeing yourself from outside, the way others do. Problem solved. Except it's not. Because when you look at that image, you're still looking from inside your own perspective. You're still you, interpreting the image through all your biases, memories, self-concepts, and expectations. When someone else looks at you, they don't have any of that. They see a stranger, a neutral face, unencumbered by your internal narrative. Studies show that people consistently rate themselves differently than others rate them. You think you look worse in photos than you do in mirrors because you're used to your mirrored reversed face. Your mirror face is more familiar, so it looks more attractive to you. But to everyone else, your non-mirrored face is the familiar one. They prefer photos because that's how they actually see you. There's also the mere exposure effect. People tend to like things they've seen more often. You see your mirror image constantly, so you prefer it. Others see your actual face constantly, so they prefer that. Neither perspective is correct. They're just different, shaped by familiarity and repetition. But it goes deeper than preference. When you look at yourself, you're always performing. Even unconsciously, you adjust your expression, your posture, the angle of your gaze. You're presenting yourself, not just observing yourself. When others look at you, they see you unguarded, in moments when you're not aware of being watched. They see micro-expressions, unconscious gestures, the face you make when you think no one's looking. You never see this face. It disappears the moment you try to observe it. Heisenberg's uncertainty principle has a psychological analog. You cannot observe yourself without changing what you're observing. The act of looking affects what you see. Your face in the mirror is your face aware of being seen. Others see your face unaware, unself-conscious, authentic in ways that vanish under your own gaze. There's also the narrative dimension. When you look at yourself, you see a life story. You see the child you were, the traumas you've survived, the hopes you carry. Your face is a text you've been writing and reading for decades. When others look at you, they see a stranger, a surface, a first impression. They don't know the story. They judge on appearance alone, at least initially. Some philosophers argue that you can never truly know yourself for this reason. Self-knowledge requires both inside and outside perspectives, but you can never fully occupy the outside perspective on yourself. You can approximate it through therapy, through honest friends, through studying how others react to you. But you can never see yourself with the fresh eyes of a stranger. Conversely, others can never fully know you either, because they lack access to your inner experience. They see behavior, appearance, effects. They infer the causes, but they don't feel what you feel, think what you think, experience what you experience. Perfect knowledge of another person might be impossible. So we're all trapped in our own perspectives, looking out at a world of other minds we can never fully access, being looked at by others who can never fully know us. The mirror promises to bridge this gap, to show us ourselves as objects, as others see us. But it can't deliver. It shows only a partial view, a frozen moment, a self-aware performance. The truth of how others see you remains forever out of reach, hidden behind the impossibility of truly stepping outside yourself. This might be lonely, or it might be liberating. You don't have to be perfectly understood to connect with others. You don't have to see yourself objectively to live authentically. The gap between perspectives creates privacy, mystery, room for interpretation. And in that gap, perhaps, is where genuine relationship becomes possible, not through perfect knowledge, but through the ongoing attempt to bridge the unbridgeable, to see and be seen despite the limitations, to reflect and be reflected in all our partial, imperfect ways. The universe reflecting on itself. Astronomer Carl Sagan once said, "We are a way for the cosmos to know itself." This is more than poetry. It's a profound observation about consciousness, observation, and reflection. For billions of years after the Big Bang, the universe existed without observers. Stars formed and died. Galaxies collided. Planets coalesced from dust. All of this happened in darkness, not because there was no light, but because there was no one to see the light. Light traveled through space, bounced off surfaces, scattered through nebulae. But without eyes to catch it, without brains to process it, without consciousness to experience it, did it matter? Was the universe in any meaningful sense observable? Then, on at least one small planet orbiting an ordinary star, chemical processes became complex enough to generate life. And life became complex enough to generate nervous systems. And nervous systems became complex enough to generate consciousness. And consciousness became sophisticated enough to turn back on itself, to observe not just the environment, but the act of observation itself. We are that turning point. We are matter that has become aware of being matter. We are the universe observing itself, locally, through biological machinery. When you look in a mirror, you're not just seeing yourself. You're seeing what happens when the cosmos becomes self-aware. The atoms in your body were forged in ancient stars. The carbon, nitrogen, oxygen, all created through nuclear fusion in stellar cores, then scattered through space when those stars exploded. You are literally made of stardust, as Sagan noted. And now that stardust has organized itself into a configuration that can look at itself, recognize itself, wonder about itself. The mirror is the universe's way of seeing its own face. This perspective dissolves the usual boundaries between self and cosmos. You think of yourself as separate from the universe, a small, temporary thing observing a vast, eternal thing. But you're not separate. You're a part of the universe that has temporarily organized into a form capable of observation. The boundary between observer and observed is arbitrary. There's only one thing, the universe. And in you, locally, it has developed the capacity for self-reflection. This has implications for consciousness itself. Some philosophers and physicists speculate that observation isn't a special add-on to physical reality. It's fundamental to it. Quantum mechanics suggests that observation collapses wave functions, that the act of measurement affects the system being measured. At the quantum level, observer and observed are entangled, inseparable. If this is true, then consciousness isn't separate from the physical universe. It's part of how the universe operates, part of the mechanism through which possibility becomes actuality, through which the wave function collapses into definite states. You, observing yourself in a mirror, are the universe causing its own wave function to collapse, creating definite reality from quantum possibility. This might sound mystical, but it's grounded in physics. The universe's ability to observe itself through conscious beings might be not just poetic, but mechanistically necessary for reality to be definite rather than probabilistic. Without observers, perhaps there are only wave functions, only potentials, only mathematical possibilities. With observers, reality crystallizes. Of course, this raises questions. Is the universe itself conscious? Is there some cosmic awareness that encompasses all local consciousnesses? Most physicists say no. Consciousness seems to emerge from specific physical configurations, not from the universe as a whole. But some, like physicist Roger Penrose, propose that consciousness might be a fundamental feature of reality, woven into the quantum structure of space-time. We don't know. What we do know is that you exist, that you're aware, that you can observe yourself and the cosmos. and that's already remarkable enough. Every time you look in a mirror, you're participating in the most extraordinary process in the known universe, matter becoming aware of itself, the cosmos waking up, the universe developing eyes and using them to see. The reflection you see is billions of years in the making. It required the formation of galaxies, the death of stars, the slow evolution of life, the development of neurons and eyes and consciousness. It required the universe to spend 13.8 billion years arranging atoms into a configuration that could look at itself and understand what it was seeing. You are that configuration. The mirror just makes it visible. Butterfly wings and structural color. Most colors you see come from pigments, molecules that absorb some wavelengths of light and reflect others. A red apple contains molecules that absorb blue and green light, reflecting red. Simple chemistry. But some of nature's most brilliant colors come from structure, not chemistry. These are called structural colors, and they work like tiny mirrors built into biological tissue. The morpho butterfly, native to Central and South American rainforests, has wings of intense, iridescent blue. This blue is so vivid it seems to glow, but there's no blue pigment in the wings. If you ground up the wing scales and looked at the powder, it would be colorless or slightly brown. The blue comes from nanoscale structures, microscopic ridges on the wing scales arranged in layers separated by precise distances. When light hits these structures, it reflects off multiple layers. Some of the reflected light waves align perfectly, their peaks and troughs matching. This is called constructive interference. Other wavelengths don't align. They experience destructive interference and cancel out. Only blue wavelengths constructively interfere, so only blue reflects strongly. The wing acts as a natural mirror that selectively amplifies certain colors. This is the same principle behind soap bubbles and oil slicks, thin film interference creating rainbow colors from colorless materials. But butterfly wings are far more sophisticated. The structures are precisely engineered at the nanometer scale, tuned to reflect specific wavelengths depending on the species. Different butterflies, different structures, different colors. Structural color has advantages over pigment. It doesn't fade as quickly. Pigments degrade with time and sunlight, but physical structures persist. It's more vibrant. Interference can produce purer, more saturated colors than chemical pigments. And it can be iridescent, changing color as the viewing angle changes. Watch a morpho butterfly in flight, and its wings flash blue, then dark, then blue again as the angle of reflected light shifts. This iridescence serves functions beyond beauty. It makes the butterfly highly visible to potential mates but difficult to track for predators. The flashing color creates a strobe-like effect that confuses the visual system of pursuing birds. Evolution discovered structural color hundreds of millions of years ago. Beetles, birds, fish, even some plants use it. Peacock feathers are structurally colored. Their brilliant blues and greens come from photonic crystals in the feather barbules, not from pigments. The structures are so precisely organized they function as biological optics labs. Scientists study these natural photonic structures to design better reflective materials. Mirrors, anti-reflective coatings, optical filters, nature solved these engineering problems long before humans existed. By analyzing butterfly wing scales, researchers have developed more efficient solar panels, better fiber optic cables, and advanced display technologies. The butterfly's wing is a library of optical engineering principles, written in chitin and air, tested by evolution, optimized over millions of generations. And it all works through reflection, light bouncing off layers at different depths, interfering with itself, creating color from geometry alone. The butterfly is a flying mirror, its wings crafted at the nanoscale to reflect only the most beautiful wavelengths. A demonstration that nature can build optical devices as sophisticated as anything humans have invented. Fish scales and camouflage. If you've ever seen a school of fish flash silver as they turn, you've seen biological mirrors in action. Fish scales contain tiny crystals of a molecule called guanine, the same guanine that's a base pair in DNA, but arranged here in reflective structures. These guanine crystals are stacked in organized layers within specialized cells called iridophores. Light reflects off these layers, and just like butterfly wings, the spacing between layers determines what colors are reflected. In many fish, the spacing is tuned to reflect all visible wavelengths equally, creating a silvery mirror effect. This is camouflage, but not the kind you might expect. The fish isn't hiding by blending into the background. It's hiding by becoming a mirror. When a predator looks at the fish from the side, it sees a reflection of the surrounding water, blue above, darker below. The fish effectively disappears, becoming indistinguishable from the environment it reflects. This is called mirror camouflage, and it's devastatingly effective in the ocean's open water where there's nowhere to hide. The mirror isn't perfect. That would make the fish too conspicuous, too shiny. Instead, fish scales are tuned to reflect just enough to blend in, but not so much that they create bright flashes that attract attention. It's a careful evolutionary balance. Some fish can adjust their reflectivity in real time. By changing the orientation or spacing of the guanine crystals, controlled by muscles and hormones, they can become more or less reflective depending on the light conditions and the threat level. This is dynamic camouflage, adaptive armor. At night, some fish become less reflective since there's little light to create the mirror effect. During the day, in bright water, they maximize reflection. Squid and cuttlefish take this even further. They have chromatophores, pigment cells they can expand or contract, and iridophores with adjustable reflectivity. By combining colored pigments with structural colors and mirrors, they can create patterns, textures, and color shifts in real time. A cuttlefish can ripple waves of color across its skin, change from brown to white in a fraction of a second, or create fake eye spots to startle predators. It's using biological mirrors as controllable display technology. The mirror principle extends to counter-illumination. Some fish and squid in the deep ocean produce bioluminescent light from their undersides. Predators looking up from below see a silhouette against the dim light filtering down from the surface. But if the animal matches the downwelling light with its own bioluminescence, the silhouette disappears. It's not reflection, but it achieves the same goal, becoming invisible by matching the light around you. Evolution has optimized these systems over hundreds of millions of years. The guanine crystals in fish scales are arranged with nanometer precision. Any misalignment and the reflection fails. The spacing is often tuned to within a few nanometers of the optimal value. This is engineering at a molecular scale, accomplished through genetic programs and developmental processes. Humans are now learning to replicate these tricks. Researchers have created artificial materials that mimic fish-scale reflectivity for stealth applications, improved mirror coatings, and even cosmetics. The shimmery effect in some makeups comes from guanine extracted from fish scales or synthetic alternatives based on the same structure. Nature invented the mirror not once but many times, in many forms, for many purposes. And wherever light exists, wherever there's an evolutionary advantage to controlling how light reflects, living things have found ways to build biological mirrors, sometimes for camouflage, sometimes for display, always through exquisite nanoscale engineering. The mirror spider. In the rainforests of Australia lives one of nature's strangest creatures, Theseus argentiopunctata, commonly known as the mirror spider or sequined spider. Its abdomen is covered in reflective silver plates that look like tiny mirrors, giving it the appearance of a living disco ball. The reflective plates are made of guanine crystals, similar to fish scales, but arranged in flat, tile-like structures on the spider's exoskeleton. The effect is dramatic. The spider's abdomen looks like it's made of polished metal or mirrored glass. And here's what makes it even stranger. The mirrors are adjustable. When the spider is threatened or agitated, the reflective plates can expand or contract. In some cases, the spider can go from fully mirrored to nearly transparent, then back to mirrored again, in a matter of seconds. The mechanism isn't fully understood, but it seems to involve fluid being pumped into or out of the space between the guanine crystals and the outer cuticle, changing how light reflects. Why would a spider want to be a mirror? Several hypotheses exist, but no consensus. One theory: the mirrors are camouflage. In the dappled light of the rainforest, reflecting the surroundings might make the spider harder to see, breaking up its outline and confusing predators. Another theory: the mirrors are a defensive signal. The sudden flash of light when the plates expand might startle predators, giving the spider time to escape. Some animals use sudden contrast or movement as a defensive display. Peacock spiders, also Australian, flash colorful patterns to deter threats or attract mates. Mirror spiders might be doing something similar. A third theory: thermoregulation. Reflective surfaces stay cooler in sunlight. By adjusting the reflectivity, the spider might be managing its body temperature. In hot conditions, become a mirror to reflect heat. In cool conditions, become transparent to absorb warmth. Or perhaps it's all three. Evolution often finds multiple uses for a single trait. The mirror serves several functions simultaneously, each providing a slight advantage, the combination justifying the metabolic cost of building and maintaining the reflective plates. What's certain is that the mirror spider represents another independent evolution of biological mirrors. Butterflies, fish, beetles, birds, squid, and now spiders all have evolved reflective structures, all using similar principles but different implementations. The laws of physics are universal. Reflection works the same way everywhere. So evolution, working blindly through mutation and selection, repeatedly discovers the same solutions. Organize transparent materials in layers, space them at specific intervals, and you get constructive interference, selective reflection, structurally flexion, structurally color. It's convergent evolution driven by physics. The mirror spider also demonstrates how spectacular biological diversity can be. There are tens of thousands of spider species, and among them is one that decided to become a mirror. Not for any grand cosmic reason, but because in the specific ecological niche of Australian rainforests, being reflective provided some small survival or reproductive advantage. And that was enough. When you look at the mirror spider, you're seeing evolution's creativity on full display, taking basic materials, organizing them at the nanoscale, creating optical devices through nothing but random mutation, filtered by survival. The spider didn't design its mirrors. Natural selection designed them, one generation at a time, refining the structure until it worked. And now there's a spider that sparkles like a jewel, that can turn its mirrors on and off, that disappears and reappears in flashes of silver light. Nature's mirrors are everywhere once you start looking, in wings and scales and shells and skin. Each one a testament to the power of evolution to engineer optical solutions, to bend light through structure, to turn living tissue into technology. Eyes as reverse mirrors. An eye is, in a sense, a reverse mirror. Instead of reflecting light outward, it captures light inward. But some eyes actually do use mirrors, and in ways that seem almost impossibly clever. Most animal eyes work like cameras. Light enters through a lens, focuses on a retina, and photoreceptor cells detect the light and send signals to the brain. But some animals have eyes that use mirrors instead of, or in addition to, lenses. The scallop, a bivalve mollusk, has dozens of tiny eyes along the edge of its shell. Each eye contains a curved mirror made of guanine crystals. Yes, the same molecule fish use for scales and spiders use for reflective plates. Light enters the eye, passes through the retina, which is partially transparent, and reflects off the mirror at the back. The reflected light focuses back onto the retina, creating an image. This is called a reflecting eye, and it's completely different from how human eyes work. We use a lens to focus light. Scallops use a mirror. The advantage? Mirrors don't suffer from chromatic aberration, the tendency of lenses to focus different colors at different distances, creating blurry edges. Mirrors focus all wavelengths to the same point. This gives scallops surprisingly good color vision despite having simple eyes. Some deep-sea fish also have reflecting eyes. The brown-snout spookfish, living at depths where light is extremely dim, has eyes that are part lens, part mirror. The upper portion uses a lens to focus downwelling light from the surface. The lower portion uses a curved mirror to focus bioluminescent light from below. Two optical systems in one eye, each optimized for different light sources. Evolution invented the reflecting telescope independently in fish millions of years before humans invented it for astronomy. Then there's the tapetum lucidum, the reflective layer behind the retina in many nocturnal animals. Cats, dogs, deer, raccoons, and many others have it. This isn't for forming images, it's for amplifying light. Light that passes through the retina without being absorbed hits the tapetum lucidum and reflects back, giving the photoreceptors a second chance to detect it. This doubles the eye's sensitivity, allowing animals to see in near darkness. It's also why their eyes glow when caught in headlights or flashlights. You're seeing light from the external source reflecting off the tapetum lucidum back out of the eye. The eye becomes a mirror, briefly, sending light back to the observer. Humans don't have a tapetum lucidum. Our eyes don't glow. We sacrificed light sensitivity for better color vision and higher acuity. But in dim conditions, animals with tapetum than we do. They're using biological mirrors to enhance their vision. Even in human eyes, though, there's reflection. The retina itself reflects some light. This is how eye doctors examine your retina with an ophthalmoscope. And in photos, the red eye effect is light from the camera flash reflecting off blood vessels in the retina and back through the pupil. Your eye is weakly reflective, even without a tapetum. The evolution of eyes is one of biology's great stories. Eyes have evolved independently at least 40 times in different lineages, and many of those evolutionary experiments included mirrors, sometimes as the primary optical element, sometimes as enhancement, sometimes as a backup system. Nature has explored nearly every possible way to manipulate light for vision. The eye and the mirror seem like opposites. One captures light, one reflects it. But in biology, they merge. The eye uses mirrors to see better. The mirror, in a sense, becomes part of vision. And both are fundamentally about the same thing, controlling light, directing it, using it to gather information about the world. When you look into the eyes of a cat at night and see them shine back at you, you're seeing a biological mirror doing what evolution designed it to do. Gather every possible photon, reflect what isn't absorbed, maximize vision in darkness. You're seeing the same physics that makes bathroom mirrors work, but repurposed by evolution for survival. The universe is full of light, and life has found every conceivable way to use it. The Great Observatories, the largest telescopes in the world, don't use lenses. They use mirrors. The reason is simple. Big lenses are heavy, expensive, and they sag under their own weight. Big mirrors can be supported from behind and polished to near perfection. The James Webb Space Telescope has a mirror 6.5 meters across, made of 18 hexagonal segments coated in gold. Gold reflects infrared light better than aluminum, and Webb observes in infrared to see the most distant, ancient galaxies whose light has been stretched by cosmic expansion. Each mirror segment was polished so precisely that if you scaled it up to the size of the United States, the largest imperfection would be just a few inches tall. This precision is necessary because telescopes detect faint light from objects billions of light years away. Any imperfection scatters light, reduces clarity, and ruins the image. The Hubble Space Telescope, perhaps the most famous observatory, also uses mirrors. When it launched in 1990, its primary mirror had a flaw. polished to the wrong shape by just 2.2 micrometers. This tiny error, about 1/50th the width of a human hair, made images blurry. Astronauts later installed corrective optics, essentially giving Hubble glasses, and it became the most productive scientific instrument ever built. Ground-based telescopes face additional challenges. Earth's atmosphere distorts light. This is why stars twinkle. To compensate, modern telescopes use adaptive optics, deformable mirrors that change shape hundreds of times per second, correcting for atmospheric turbulence in real time. The mirror flexes, countering the atmosphere's distortions, producing sharp images despite looking through miles of turbulent air. These mirrors are controlled by computers analyzing light from guide stars. The system measures how the atmosphere has distorted the light, calculates the correction needed, and adjusts the mirror instantly. It's like having a mirror that learns, that responds, that actively fights against imperfection. Why do we build such elaborate mirrors? Because we want to see. We want to know what's out there. Distant galaxies, exoplanets, the cosmic microwave background. Mirrors gather ancient light, focus it, deliver it to detectors. Every photon that traveled billions of years across space ends its journey on a mirror, carefully crafted by human hands, revealing secrets of the universe's birth and fate. The laser's perfect bounce. A laser requires mirrors, not just any mirrors, but nearly perfect ones. The word laser stands for light amplification by stimulated emission of radiation. Here's how it works. Atoms are excited to high energy states, then release photons in a cascade. These photons bounce between two mirrors, stimulating more atoms to release more photons, all in phase, all the same wavelength. The light builds, amplifies, and eventually exits through one partially transparent mirror as a coherent beam. Without mirrors to trap and reflect the light, there's no amplification. The photons would just scatter randomly. The mirrors create an optical cavity where light bounces back and forth, building intensity with each pass until it reaches threshold and bursts out as a laser beam. Laser mirrors must be extraordinarily reflective, often 99.9 or higher. Even 0.1 loss per bounce adds up quickly. After 1,000 bounces, most of the light would be gone. High-power lasers require mirrors that reflect 99.9 or better, with coatings engineered at the atomic scale to minimize absorption and scattering. These mirrors also must withstand intense energy. Industrial cutting lasers generate kilowatts of power focused into tiny spots. Even a small imperfection can absorb enough energy to heat, crack, or destroy the mirror. Mirror damage is one of the main limitations on laser power. Lasers have transformed technology. Surgery uses them to reshape corneas or cut tissue with precision impossible for scalpels. Manufacturing uses them to cut metal, weld parts, engrave circuits. Communications use them to transmit data through fiber optic cables at light speed. Scientists use them to measure distances with millimeter precision. The Lunar Laser Ranging Experiment placed mirrors on the Moon during Apollo missions. Scientists on Earth fire lasers at these mirrors and measure the time for light to return. This tells us the exact distance to the Moon, currently about 384,400 kilometers, but increasing by 3.8 centimeters per year as the Moon slowly drifts away. That's astonishing precision, measuring continental drift on the Moon, using light bounced off mirrors left by astronauts over 50 years ago. Every technology from barcode scanners to DVD players to laser pointers relies on mirrors creating, directing, or controlling coherent light. The laser transformed the 20th century, and it's built fundamentally on reflection. Light bouncing between mirrors, amplifying, organizing into coherent beams that cut, measure, communicate, and illuminate. Fiber optics and the flexible mirror. Light normally travels in straight lines, but fiber optic cables bend light around corners, through loops across thousands of kilometers. How? Through total internal reflection, a phenomenon where light doesn't just reflect, it's trapped. When light travels from a dense material like glass into a less dense material like air, it bends away from the perpendicular. But if the light hits the boundary at a steep enough angle, it can't escape. It reflects completely, with 100 efficiency. This is total internal reflection, and it's the principle behind fiber optics. A fiber optic cable is a thin strand of ultra-pure glass, surrounded by a cladding layer with a lower refractive index. Light entering one end bounces off the core cladding boundary repeatedly as it travels through the cable. Each bounce is a perfect reflection. The light zigzags down the fiber, trapped inside, unable to escape. These cables carry nearly all internet traffic. Data converts to light pulses that travel through glass at about 2/3 the speed of light in vacuum. A single fiber can carry terabits per second, enough bandwidth for millions of simultaneous video streams. And because the reflection is total, very little light is lost. Modern fibers can transmit light over 100 kilometers before needing amplification. The glass is so pure that if the ocean were made of it, you could see the bottom of the Mariana Trench. Fiber optics also enable medical endoscopes, flexible cables that carry light into the body and images back out, allowing surgeons to see inside patients without large incisions. The same principle, total internal reflection trapping light in flexible glass strands. What's remarkable is that fiber optics transform rigid, straight-line light into something flexible and controllable. The mirror becomes not a surface but a boundary, not flat but curved along the fiber's entire length. Light that should travel straight is convinced to follow curves, bends, loops, all through the physics of reflection. This technology connects the world. Undersea cables, each containing hundreds of fiber strands, link continents. Your internet traffic has probably bounced through thousands of kilometers of fiber, reflected millions of times off glass boundaries, traveling near light speed, carrying information as pulses of reflected light. The mirror, stretched into a thread woven into networks, has become the nervous system of global civilization. Gravitational wave mirrors. In 2015, humanity detected gravitational waves for the first time, ripples in space-time itself, caused by two black holes colliding over 1 billion light-years away. The detection required the most precise mirrors ever made. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses mirrors to measure distortions in space-time smaller than a proton. Here's how it works. A laser beam splits and travels down two perpendicular arms, each 4 kilometers long. At the end of each arm is a mirror. The light bounces off the mirrors and returns. If space-time is undistorted, the two beams arrive back in perfect sync. But when a gravitational wave passes through, it stretches space in one direction and compresses it in the other. One arm becomes slightly longer, the other slightly shorter. The light travels different distances, and when the beams recombine, they're slightly out of phase. This phase difference is detected as a change in brightness. The precision required is insane. LIGO detects changes in arm length of about 10 to the power of -18 meters, 1,000th the diameter of a proton. This means the mirrors must be nearly perfect. They're made of ultra-pure fused silica, polished to within a few atoms of perfect smoothness. They're coated with dozens of alternating layers of materials, each layer precisely thick to maximize reflectivity. The coatings reflect 99.99999 of the light. Even with this precision, LIGO must isolate the mirrors from all vibrations. Earthquakes, ocean waves, passing trucks, even thermal noise from random atomic motion, all must be filtered out. The mirrors hang on sophisticated suspension systems that dampen vibrations, allowing only gravitational waves to affect the measurement. These mirrors have opened a new window on the universe. We now detect black hole mergers, neutron star collisions, events that emit no light but warp spacetime itself. The mirrors don't see light from these events. They see the stretching and compressing of space, the ripples in reality's fabric. In a sense, these are the ultimate mirrors. They don't reflect electromagnetic waves. They reflect gravitational waves, distortions in the geometry of the universe itself. And they're so sensitive that they've detected dozens of cosmic collisions, each billions of light years away, each warping spacetime by amounts smaller than atoms. Mirrors evolved from polished bronze to silvered glass to quantum-engineered multi-layer coatings. Now they detect the universe's deepest vibrations, proving Einstein's final major prediction, revealing a cosmos more violent and dynamic than we imagined. The solar mirror and megastructures. Imagine a mirror the size of a planet or a star. This isn't science fiction, it's speculative engineering called a Dyson sphere, proposed by physicist Freeman Dyson in 1960. Advanced civilizations might build enormous structures around their stars to capture all the star's energy output. One version uses mirrors, giant reflective panels orbiting the star, focusing light toward collectors or habitats. The energy available from a star is staggering. The sun outputs about 3.8 times 10 to the power of 26 watts. Earth receives only about a billionth of this. A Dyson sphere would capture it all, providing energy for a civilization millions of times more powerful than ours. Building such a structure would require dismantling planets for raw materials and deploying mirrors across billions of square kilometers. It's beyond current technology, but not beyond physics. Some astronomers search for Dyson spheres by looking for stars with unusual infrared signatures, waste heat from the structure, or strange dimming patterns as the mirrors orbit. So far, no confirmed detections, but the search continues. On a smaller scale, solar sails use mirrors for propulsion. Lightweight reflective sheets catch photons from the sun. Each photon imparts a tiny push when it reflects. Millions of photons create measurable thrust, accelerating the sail slowly but continuously. Unlike rockets, solar sails need no fuel. They're pushed by light itself. Japan's Icaros spacecraft successfully tested solar sail technology in 2010, using photon pressure to adjust its trajectory. Future missions might use powerful lasers on Earth or in orbit to push light sails to nearby stars, potentially reaching a significant fraction of light speed. The mirror becomes an engine, turning reflected light into motion. Mirrors could also cool planets. Proposals for combating climate change include placing mirrors at the lone Lagrange point between Earth and Sun, reflecting a small percentage of sunlight away to reduce heating. This is geoengineering on a massive scale, using mirrors to control planetary temperature. All of these ideas, energy collection, propulsion, climate control, use the same principle. Reflection redirects energy. A mirror doesn't create energy. It moves it, focuses it, uses it for purposes nature never intended. As humanity reaches for the stars, mirrors will likely come with us, gathering solar energy, pushing spacecraft, protecting planets. The simple act of reflection, discovered in ancient pools, refined through medieval craftsmanship, understood through quantum mechanics, now scales up to cosmic engineering. The mirror is one of our oldest technologies and potentially one of our most powerful. The one-way mirror illusion. You've seen them in police dramas, interrogation rooms where detectives watch through a one-way mirror while the suspect sees only their reflection. But here's the truth. One-way mirrors don't exist. What you're seeing is a two-way mirror, glass coated to be partially reflective, exploiting a difference in lighting. Here's how it works. The mirror coating reflects about 50 of light and transmits 50. If you're in a brightly lit room looking at it, most of the light hitting your eyes is reflected from your side. You see yourself. The transmitted light from the dark room behind the glass is too faint to see. But someone in the dark room looking out sees the opposite. The bright light from your room transmits through the glass easily. The darkness of their room means little light reflects back. They see through clearly. It's all about light intensity ratio. Make both rooms equally bright, and the one-way mirror becomes transparent from both sides. Make the mirror side darker, and it reverses. Now the formerly hidden observers see reflections while the formerly observed can see through. There's no magic, no special physics. It's just selective transparency exploiting human perception. This same principle is used in sunglasses, building windows and camera lenses. The coating is called a half-silvered mirror or beam splitter. Photographers use them to create double exposures. Scientists use them in interferometers, devices that split light beams, send them on different paths, then recombine them to measure tiny differences. The famous one-way mirror is a reminder that our perception of mirrors depends heavily on context, lighting, angles, coatings. Change the context, and what seemed like a clear reflection becomes a window, or vice versa. The boundary between seeing and being seen, between transparency and reflection, is thinner and more contingent than we realize. Most mirrors in daily life are front surface mirrors. The reflective coating is on the front. But two-way mirrors are back surface mirrors with partial coating. Touch them and your finger has a gap from the reflection because the glass is in between. This is one way to detect them. Or just change the lighting and watch the magic disappear. The invisible mirror and metamaterials. What if you could make a mirror invisible? Not by hiding it, but by bending light around it so smoothly that it leaves no trace. This is the goal of metamaterial research, engineering materials with properties that don't exist in nature. Metamaterials are structured at scales smaller than the wavelength of light, with carefully designed geometries that control how electromagnetic waves propagate. By arranging metals and dielectrics in precise patterns, researchers can create materials with negative refractive index, meaning light bends the wrong way when entering them. With negative refraction, you can theoretically build a cloak. Light approaching an object would bend around it, guided by the metamaterial's structure, and emerge on the other side as if the object weren't there. To an observer, the object would be invisible, not because it's transparent, but because light is routed around it. This has been demonstrated in laboratories at microwave frequencies and, more recently, at visible wavelengths for very small objects. The technology is still primitive, cloaking a grain of sand under specific lighting conditions, but the principle works. The mirror becomes anti-mirror. Instead of reflecting light, it guides light around itself, becoming undetectable. Metamaterials also enable superlenses, lenses that can resolve features smaller than the wavelength of light, breaking the diffraction limit that normally prevents seeing details below about 200 nanometers with visible light. These use negative refraction to capture and focus evanescent waves that normally decay before reaching a detector. The applications are profound. Imagine microscopes that see individual molecules, optical computers that manipulate light at nanoscales, or stealth technology that makes objects genuinely invisible. We're not there yet, but the physics is sound. The challenge is engineering, building structures with nanometer precision across large areas. Nature provides hints. Some butterfly wings and beetle shells have photonic structures that approach metamaterial behavior. Evolution discovered some of these tricks millions of years ago. But human-made metamaterials can go further, creating optical properties impossible in biology. The invisible mirror is a paradox, a reflective surface that doesn't reflect because it hides itself through bending light. It's the ultimate evolution of mirror technology, so advanced that it erases its own existence, leaving only the light that passes through as if nothing were there. The perfect absorber. The opposite of a mirror is a perfect absorber, a surface that reflects nothing, absorbing all light that hits it. This is harder to achieve than you might think. Most black materials still reflect a few % of light. True blackness requires extraordinary engineering. Vantablack, developed for aerospace applications, absorbs 99.96% of visible light. It's made of carbon nanotubes, tiny tubes of carbon atoms grown vertically on a substrate. Light entering the nanotube forest bounces between tubes, getting absorbed with each bounce until almost none escapes. The result is a material so black that textured surfaces appear completely flat. All depth information vanishes. A crumpled piece of vantablack-coated aluminum foil looks like a flat black void. Your visual system can't process it. There are no shadows, no highlights, no cues to shape. It's deeply unsettling to look at. Scientists have since created even blacker materials. Researchers developed a carbon nanotube array that absorbs 99.995% of light. At this level, the material is blacker than any natural substance. It's a black hole for photons, nearly perfect absorption. Why build such materials? For telescopes and cameras. Stray light reflecting inside instruments creates noise and reduces image quality. Perfect absorbers eliminate stray reflections, improving sensitivity. They're also used in solar panels to maximize energy capture and in stealth technology to minimize radar signatures. But perfect absorption has a cost. The absorbed light becomes heat. A vantablack surface in sunlight heats up rapidly. The photons don't disappear. Their energy converts to thermal energy. This is the second law of thermodynamics in action. Energy changes form but never vanishes. The perfect absorber is the mirror's shadow twin. Where mirrors reflect all and absorb nothing, perfect absorbers do the opposite. Together, they define the extremes of optical behavior. Most materials fall somewhere in between, partially reflective, partially absorptive. But these extremes show what's possible when you engineer materials with precision, and they reveal a deeper truth. Light always does something when it hits matter. It reflects, absorbs, transmits, or scatters. There's no fifth option. The perfect absorber chooses total absorption, and in doing so becomes invisible in a different way than metamaterial cloaks. It doesn't bend light around itself. It swallows light completely, becoming a void, an absence, a hole in the visible world. Adaptive optics and mirrors that learn. Imagine a mirror that watches the stars and changes its shape to compensate for atmospheric turbulence. This exists, it's called adaptive optics, and it's how modern telescopes overcome Earth's blurry atmosphere. Stars twinkle because atmospheric turbulence bends their light erratically. To a telescope, this makes stars look blurred and fuzzy. But if you could change the telescope's mirror shape hundreds of times per second, matching the atmosphere's distortions, you could cancel out the blurring. Adaptive optics systems use deformable mirrors, thin reflective surfaces backed by actuators that can push and pull to change the mirror's shape. A computer analyzes light from a bright guide star, measures the atmospheric distortion, and calculates the correction needed. The actuators adjust the mirror accordingly, and suddenly the blurred star becomes sharp. This happens in real time. The atmosphere changes constantly, so the mirror must change constantly too. Modern systems adjust at up to 2,000 times per second, faster than the atmosphere can shift. The result is images as sharp as if the telescope were in space. These mirrors are learning systems in a sense. They observe, measure, calculate, and adapt. They're not conscious, but they respond intelligently to changing conditions. This is the future of optics, active rather than passive, smart rather than inert. The same technology is being explored for other applications. Adaptive mirrors in laser systems could correct for thermal distortions, improving beam quality. In microscopy, they could compensate for imperfections in samples, improving resolution. In displays, they could create 3D images by controlling wavefronts. The mirror is evolving from a static object to a dynamic tool, from something that simply reflects to something that reflects intelligently, adjusting in real time to serve its purpose better. This is technology becoming responsive, alive in a limited sense, sensing and adapting to the world. And it raises a question: how much smarter can mirrors become? Could we build mirrors that predict atmospheric changes before they happen? Mirrors that self-repair when scratched? Mirrors that reconfigure themselves for different tasks? The adaptive mirror is a glimpse of a future where materials aren't passive but active, where surfaces don't just sit there but respond, learn, and optimize. The ancient mirror showed us our faces. The smart mirror might someday show us the universe with perfect clarity, adapting faster than we can think, learning the sky's moods, becoming an intelligence of its own. The cosmic microwave background. The universe has a mirror, and it surrounds us completely. It's called the surface of last scattering, and it's where light first became free to travel through space. In the early universe, everything was too hot and dense for light to travel far. Photons would scatter off electrons constantly, unable to make any progress. The universe was opaque, a glowing fog of plasma. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into hydrogen atoms. Suddenly, photons could travel freely. This moment, recombination, created a spherical surface in spacetime. Light from that surface has been traveling toward us ever since. This light is the cosmic microwave background, or CMB. It's the oldest light in the universe, the afterglow of the Big Bang. And it comes from every direction, a spherical mirror surrounding Earth, showing us what the universe looked like when it was just a baby. The CMB has been stretched by cosmic expansion. What was once visible light is now microwave radiation, invisible to human eyes but detectable by specialized telescopes. Maps of the CMB show tiny temperature variations, hot and cold spots that are the seeds of all cosmic structure, galaxies, galaxy clusters. Everything formed from those initial density fluctuations. We're seeing the blueprint of the universe. But here's the profound part. We can never see beyond this surface. The universe before recombination is invisible, not because it's too far away, but because light couldn't travel through the plasma. The surface of last scattering is an absolute barrier to optical observation. It's the universe's ultimate mirror, reflecting the earliest moment we can ever hope to see. Looking at the CMB is like standing inside a spherical mirror. Everywhere you look, you see the same ancient light, slightly warped by your position in spacetime. You're seeing the past, not of a distant object, but of the universe itself, the moment it became transparent, reflected in all directions, surrounding you completely. And as we look deeper into space, we're looking back in time, approaching that mirror, seeing the universe younger and younger until we reach the wall of light that marks the beginning of visibility itself. Light echoes across time. In 1572, astronomer Tycho Brahe observed a supernova, a star exploding in the constellation Cassiopeia. The light from this explosion traveled across space and reached Earth, where it was recorded by observers. Then it faded. But the explosion's light didn't only travel toward Earth. It traveled in all directions. Some of it hit interstellar dust clouds far from the explosion. And years later, centuries later, that reflected light reaches us, like an echo arriving long after the original sound. This is called a light echo, and it's one of the strangest phenomena in astronomy. Light from a transient event, a supernova, a stellar outburst, reflects off dust clouds at various distances. Because the reflected light travels a longer path, it arrives later. We see the same event multiple times, from different angles, separated by years or even centuries. Modern astronomers have observed light echoes from Tycho's supernova more than 400 years after the original explosion. By studying these echoes, they can analyze the supernova's spectrum, understand its chemistry, and learn about the explosion mechanism, all from an event that happened when Shakespeare was alive. Light echoes also occur around variable stars and novae. The star brightens briefly, light races outward, hits surrounding dust, and reflects back toward us months or years later. We see nested shells of light, like ripples on a pond, frozen in time by the geometry of space and the finite speed of light. This reveals something beautiful about the universe. Light's journey doesn't end when it reaches our eyes. It continues, bouncing off dust, reflecting off nebulae, scattering through gas. Every photon that doesn't get absorbed keeps traveling, keeps reflecting, potentially forever. The universe is filled with ancient light still bouncing around, light from long-dead stars, light from events billions of years past. Some of that light might eventually reach Earth, arriving as unexpected echoes from cosmic history. Light echoes are natural time machines. They let us see past events from new angles, study explosions long over, analyze stellar outbursts that occurred before we had telescopes. The universe preserves its history in reflected light, scattered across space, waiting for observers to catch it. And in a sense, every observation is a light echo. The light you see from any star is old. It left years, centuries, or millennia ago. You're seeing the past, always. The star might not even exist anymore, but its light continues, reflecting off you, entering your eyes, making the star visible long after it died. The Photon Sphere. Near a black hole, there's a region where light can orbit. Not fall in, not escape, just orbit, circling forever. This is called the Photon Sphere, and it exists at 150 times the Schwarzschild radius, the boundary of the event horizon. At this precise distance, space-time is curved so severely that light traveling tangentially follows a circular path. A photon entering this orbit will circle the black hole endlessly, trapped by gravity alone, no physical surface needed. If you could somehow survive at the Photon Sphere and look to the side, you'd see the back of your own head. Light from you would circle the black hole and return. You'd see multiple images of yourself, one from light that circled once, another from light that circled twice, and so on. Each image smaller and more distorted. You'd be surrounded by infinite copies of yourself, nested like Russian dolls, each one a ghost from the past, because each image shows you as you were when that light left, a fraction of a second or several orbits ago. This creates a natural hall of mirrors, built from gravity and geometry alone. The photon sphere is unstable. A photon in a perfect circular orbit will stay there forever, but the slightest perturbation, a gravitational wave, a passing particle, will knock it inward toward the event horizon or outward into space. Real photon orbits don't last, but theoretically, they exist, defining a boundary where light transitions from escapable to doomed. Black holes aren't truly black. They emit Hawking radiation, a quantum effect where particle-antiparticle pairs form near the horizon, and one escapes while the other falls in. Over unimaginably long timescales, black holes evaporate completely. But while they exist, they're the universe's most extreme mirrors, not reflecting light but trapping it, bending space-time so severely that light loops back on itself. Observing the photon sphere is nearly impossible. It's hidden just outside the event horizon, and any light we detect has already escaped. But the Event Horizon Telescope, which captured the first image of a black hole's shadow in 2019, revealed a bright ring around the darkness, light from the photon sphere, and just beyond, bent by gravity, creating a halo of trapped and escaping photons. The photon sphere is where geometry becomes fate. Light that would normally travel straight forever is bent into circles, imprisoned by curvature, reflecting the black hole's presence through pure gravitational power. The heat death and the last reflection. The universe is expanding. Galaxies are moving apart. Stars are burning out. And eventually, in the unimaginably distant future, the universe will reach heat death, a state of maximum entropy where all energy is evenly distributed. All gradients are gone, and no work can be done. At that point, no more stars will form. No more light will be emitted. The universe will be cold, dark, and empty, filled with black holes slowly evaporating through Hawking radiation, releasing their mass as faint thermal radiation over timescales of 10 years or more. Eventually, even the black holes will disappear. And then there will be only photons, low-energy radiation spread across an ever-expanding universe, cooling toward absolute zero as space stretches. These photons will be the last light, the final reflections of a universe that once burned bright. But even this light will fade. As the universe expands, wavelengths stretch. Photons lose energy. What was once visible light becomes infrared, then microwave, then radio, then wavelengths so long they're barely distinguishable from the vacuum itself. The last reflections will become whispers, then silence. No more mirrors because no more structure. No more surfaces to reflect light. No more observers to see reflections. Just a thin soup of particles and radiation, spreading out, cooling down, approaching equilibrium. Entropy wins. The second law of thermodynamics, which we saw earlier when discussing absorbed light becoming heat, plays out on the largest possible scale. The universe trends toward disorder, toward uniformity, toward the state where nothing interesting can happen. Every reflection you've ever seen, every mirror, every surface, every glint of light exists because the universe is far from equilibrium. There are hot things and cold things, structure and void, energy gradients that allow work and observation. Heat-death erases all of that. It's a strange fate for a universe that began in perfect order, a singularity of infinite density and temperature. From that starting point, entropy has only increased. Stars burn, planets form, galaxies collide, light reflects, all processes that increase entropy globally, even as they create local pockets of order. And eventually, the increase will complete. Maximum entropy, maximum disorder. Heat death, but that's trillions upon trillions of years away. For now, stars still shine. Mirrors still reflect. And we exist in this brief, brilliant window where the universe has enough structure for light to bounce, for eyes to see, for consciousness to observe the cosmos and understand its fate. The eternal return. Some cosmologists propose that the universe might not end with heat death. Instead, it could undergo conformal cyclic cosmology, a theory by physicist Roger Penrose suggesting the universe experiences infinite cycles. In this model, the far future's heat death, a state of maximum entropy, no matter, only radiation, becomes indistinguishable from the Big Bang's initial state. With no matter to define scale or time, the infinite cold future of one cosmic eon smoothly transitions into the hot, dense beginning of the next. The universe reflects itself across time, endlessly. Each cycle produces galaxies, stars, black holes, perhaps life. Each cycle ends in heat death. Each heat death becomes a new Big Bang. The cosmos is eternal, not through stasis but through repetition, infinite variations on the same theme. If this is true, then every reflection you see is not just photons bouncing off electrons. It's part of an eternal pattern, a cosmos that reflects itself endlessly through time, each on a mirror of the last and the next. This idea resonates with ancient philosophies. Nietzsche's eternal recurrence proposed that everything happens infinitely many times. Hindu and Buddhist cosmologies describe cycles of creation and destruction. Penrose's theory gives this a modern physics-based framework. The evidence is speculative. Penrose points to anomalies in the cosmic microwave background that might be Hawking points, traces of black holes from the previous eon. Other physicists are skeptical. But the mathematics is consistent with general relativity, and the theory is falsifiable through observations. Whether or not cyclic cosmology is correct, it offers a poetic closure to our story of mirrors. We began with humans seeing their reflections in water, local, small, personal. We end with the universe itself as a mirror, reflecting across infinite time, each eon showing the next what it was and what it will become. The simple phenomenon of reflection, which seems so mundane when you check your appearance before leaving the house, scales up to encompass the entire cosmos, past, present, and future. Reflection isn't just a property of matter. It's a property of existence itself. Light reflects off surfaces. Space-time reflects gravitational waves. The universe might reflect itself across eons. And consciousness, arising from matter, observing matter, is the universe reflecting on itself. Locally, briefly, before dissolving back into the cycle. Every mirror you look into is a tiny piece of this vast pattern, a local instantiation of a cosmic principle. The face looking back at you is stardust that learned to see itself, to recognize itself, to wonder about itself. And that wondering is perhaps the universe's highest achievement, the moment when reflection becomes recursive, when the cosmos doesn't just bounce light, but contemplates the meaning of the bounce. What you're really seeing. We've traveled far together, from ancient pools to quantum mechanics, from neuroscience to cosmology, from the first obsidian mirrors to gravitational wave detectors. Now let's return to the simplest thing, you, standing in front of a mirror. What are you actually seeing? You're seeing photons that left a light source, bounced off your face, traveled to the mirror, interacted with free electrons in the metal coating, were re-emitted as new photons, traveled back across space, entered your eyes, struck your retina, triggered chemical reactions in photoreceptor cells, sent electrical signals through your optic nerve, and were processed by your visual cortex into the experience of seeing. You're seeing the past, yourself as you were nanoseconds ago. You're seeing information, not substance. The you in the mirror isn't you. It's a pattern of light that happens to carry information about how your surface looked a moment ago. You're seeing yourself from outside, an impossible perspective you can never truly occupy. You're seeing what you're telling yourself you look like, filtered through expectations, self-concept, mood, and memory. You're seeing photons that were created by electrons in the mirror responding to photons that were reflected by your skin, responding to photons that came from the sun or a light bulb, a chain of interactions going back to nuclear fusion in stellar cores or electrical currents in wires. You're seeing the universe observing itself through the temporary pattern we call you. All of this, the physics, the neuroscience, the philosophy, the history, hides in the simple act of looking. The mirror on your wall contains quantum mechanics, relativity, thermodynamics, evolution, consciousness, and cosmic history. It's mundane and miraculous simultaneously. This is the power of deep attention. When you really examine anything, mirrors, water, light, atoms, you find the entire universe reflected in it. Nothing is truly separate. Everything connects to everything else through physics, through chemistry, through history. The mirror is a reminder. What seems simple is complex. What seems familiar is strange. What seems obvious hides profound mysteries. And perhaps that's the real lesson. Not just what mirrors are or how they work, but what it means to look deeply, to question, to explore, to find wonder in the everyday. The mirror's gift. What has the mirror given humanity? Self-awareness, certainly. The ability to see ourselves as others see us, to recognize our physical presence in the world. But more than that, the mirror gave us a tool for introspection. When you look at yourself, you don't just see a face. You see evidence of time, passing, aging, changing, the visible record of life lived. You see your emotions reflected back, making feelings visible. The mirror externalizes the internal, makes the subjective observable. This accelerated human development in countless ways. Art became more realistic when artists could study their own faces for portraits. Medicine improved when doctors could see patients' symptoms and their own appearances. Social interactions became more sophisticated when people could prepare how they'd be perceived. The mirror also enabled scientific progress. Telescopes use mirrors to gather light from the cosmos. Microscopes use mirrors to illuminate the microscopic. Lasers use mirrors to amplify light. Fiber optics use mirrors to transmit information. From astronomy to biology to telecommunications, mirrors are foundational technology. But perhaps the mirror's greatest gift is psychological. It gave us the ability to think about ourselves as objects, to develop self-consciousness, to recognize that we have an appearance, an identity, a presence in the world. This is both burden and liberation. It creates anxiety. How do I look? What do others think? But it also creates agency. You can change how you present yourself. You can use your appearance as a tool for navigating social reality. The mirror made possible the concept of personal identity as we understand it today. Before mirrors, identity was mostly about role, family, status. After mirrors, identity became about self-image, self-concept, individual appearance. We became more individualistic, more self-focused, more aware of ourselves as unique entities. Some criticize this as narcissism. Others celebrate it as self-knowledge. Both are probably true. The mirror is neutral. It's a tool. How we use it determines whether it serves vanity or wisdom. Used wisely, the mirror is a teacher. It shows you reality without judgment. It reveals change, marks time, makes visible what you might prefer to ignore. It's honest in a way few things are. The reflection doesn't lie, doesn't flatter, doesn't spare your feelings. And that honesty, however uncomfortable, is valuable. The question that remains, after everything we've explored, one question persists: why does reflection exist at all? This might seem strange to ask. Reflection is just what happens when light hits a surface. It's physics. It's inevitable. But why is physics the way it is? Why do electromagnetic waves reflect at all? Why is there conservation of energy, requiring light to either reflect, absorb, or transmit? Why can't light just disappear? The answer takes us to the deepest structure of reality. Reflection exists because of conservation laws, conservation of energy, momentum, and angular momentum. These aren't arbitrary rules. They arise from fundamental symmetries in the universe. Emmy Noether proved in 1915 that every conservation law corresponds to a symmetry. Conservation of energy comes from time symmetry. The laws of physics don't change over time. Conservation of momentum comes from space symmetry. The laws of physics are the same everywhere. These symmetries are woven into the fabric of reality. And from them, all the rules we call physics emerge. Reflection is one consequence. When light hits matter, energy must be conserved. The light can't just vanish. It has to go somewhere, reflect, absorb as heat, transmit through. The specific percentages depend on the material's properties, but the total must sum to 100. Reflection isn't optional. It's required by the universe's mathematical structure. This is profound. The mirror on your wall works because the universe has symmetries. Time flows uniformly. Space is uniform. Energy is conserved. And from these abstract mathematical principles, concrete phenomena emerge. Photons bouncing off silver atoms. Images forming, you seeing yourself. Could a universe exist without reflection? Perhaps, but it would need very different symmetries, different conservation laws, different physics. It's hard to imagine what such a universe would be like. Without reflection, light would only absorb or pass through. No mirrors, no echoes, no bounce. Vision might be impossible. Eyes rely on reflected light. Communication might work differently. The universe would be alien, dark, incomprehensible. We live in a universe where reflection is possible, because we live in a universe with certain symmetries. And those symmetries might themselves be necessary for any structured reality to exist. Without conservation laws, without predictable physics, nothing stable could form. No atoms, no stars, no planets, no life. Reflection is a small consequence of vast cosmic architecture. But it's not trivial, it's essential. The fact that you can see yourself in a mirror connects directly to the deepest truths about reality, symmetry, conservation, the mathematical structure underlying existence. The question that remains isn't really why does reflection exist, but why does the universe have the structure it has? And that's the ultimate mystery. The question science approaches but may never fully answer. The next mirror. What comes after the mirror as we know it? Technology is already pushing boundaries. Smart mirrors display information, read health metrics, connect to the internet. Augmented reality mirrors can show you how you'd look with different hairstyles, clothes, or makeup before you make changes. In the future, mirrors might become fully interactive displays, seamlessly blending reflection with digital enhancement. But there are deeper possibilities. Quantum mirrors that use entangled photons to create images that can't be intercepted or copied. Temporal mirrors that reflect light across time instead of space, allowing you to see yourself as you were or will be. Gravitational mirrors we build ourselves, massive structures in space that bend light for cosmic engineering projects. And beyond technology, there's conceptual evolution. We've learned to see ourselves in new ways, through brain scans showing neural activity, through genetic sequencing revealing our molecular blueprint, through social media creating digital reflections of our lives. Each is a kind of mirror, showing aspects of ourselves previously invisible. The psychological mirror is evolving too. Therapy, meditation, journaling, all are ways of reflecting on yourself, of seeing your thoughts and behaviors from outside. The external mirror showed us our faces. These internal mirrors show us our minds. As we develop AI and machine learning, we might create mirrors that reflect not just appearance but personality, predicting our behaviors, showing us patterns we can't see ourselves. These algorithmic mirrors could reveal biases, habits, and tendencies, making visible the unconscious. And in the far future, perhaps we'll build mirrors that show alternate timelines, parallel universes, or simulated realities. Perhaps we'll use quantum technology to observe ourselves in superposition states, seeing multiple potential futures simultaneously. Or perhaps the ultimate mirror is one we're already using, the universe itself. When we study cosmology, we're looking back at our origins. When we explore biology, we're examining ourselves at the molecular level. When we create art or science or philosophy, we're reflecting on what it means to be conscious, to exist, to matter. The next mirror might not be a physical object at all. It might be a mode of understanding, a way of seeing that integrates all perspectives, inner and outer, past and future, individual and cosmic. We began this journey with a human seeing their face in water. We might end it with humanity seeing itself clearly in the universe's vast mirror, understanding finally what we are and where we came from. Stand in front of a mirror. I want to leave you with an invitation. After listening to this journey through the science and philosophy of mirrors, go stand in front of one. Look at your face. But this time, see it differently. See the atoms that make up your skin, forged in ancient stars, cycling through your body, replaced constantly yet maintaining pattern. See the light bouncing off you, photons created by excited electrons, traveling at the cosmic speed limit, carrying information. See the mirror's metal coating, silver atoms with free electrons responding to electromagnetic fields, absorbing and re-emitting light in perfect synchronization to create your image. See the 8 nanoseconds of delay. You're looking at the past, always, never the present. See the quantum superposition collapsing with each photon detected, probability becoming certainty, wave functions crystallizing into definite reality. See yourself as others see you, or try to, knowing you can never fully succeed, trapped always in your own perspective. See the consciousness looking back, the universe observing itself, matter that has become aware enough to recognize its own reflection. See the mystery of identity, the same person you were as a child, yet completely different. Every atom replaced, every cell renewed, continuous only through pattern and memory. See the philosophical questions. What is the self? What is perception? What is real? See the history, Thousands of years of mirror making, from obsidian to silver to quantum-engineered coatings. The human drive to see ourselves reflected in ever greater clarity. See the future, technology we haven't imagined, mirrors we haven't built, ways of seeing ourselves we haven't discovered. And then, just see yourself. Not the science, not the philosophy, just you. In this moment, looking. The face that's uniquely yours, the expression that's constantly changing, the self that's both observer and observed. This is what the mirror gives us. Not answers, but questions. Not certainty, but wonder. Not just an image, but a reminder that we are part of something vast and strange. A universe that has somehow, in this tiny corner of space and time, developed the capacity to reflect on itself. You are that reflection. Looking back at yourself across billions of years of cosmic evolution, seeing stardust arranged in a pattern that can see, can think, can wonder. Thank you for taking this journey through the story of mirrors. If you've enjoyed exploring these ideas, consider subscribing for more deep dives into science and wonder. Leave a comment about what surprised you most, or what you'd like to explore next. And the next time you pass a mirror, and you will, many times, maybe pause for just a moment. Look, see, wonder. Because in that simple reflection lies everything. Physics and philosophy, past and future, the mundane and the miraculous. The mirror shows us ourselves. And in ourselves, we find the universe.